Hey guys, welcome to this LangChain crash course for beginners. If you're curious about building AI applications, then you are in the right place. Whether you're a developer, entrepreneur, or just somebody interested in AI, this course is for you. And by the end of this crash course, we're going to solve real business problems by building our own RAG chatbots, creating our own agents and tools, automate tasks using LangChain, and a lot more. If you haven't heard of these terminologies, don't worry, we're going to be starting from the very basics of LangChain, right from what is LangChain, why is it used, and build our way up step by step. You can find different sections of the course below the video here. And if you ever get stuck, all the code that we'll be writing is available in the GitHub repository. The link is in the description below. If you're new to my channel, I'm Harish Neil. I've worked in software development and AI roles at companies like Freshworks, Zoho, Samsung. I also have a degree in machine learning and artificial intelligence from BITS Pilani as well. And more importantly, I love this stuff and I'm excited to share it with you. If you want to connect with me or clear up any doubts or get stuck anywhere, I've got a free community where you can find like-minded driven AI developers, founders, freelancers, even free webinars on latest AI developments. It's really a place where you can network, learn, and maybe even kickstart your next big opportunity. The link is in the description below. So with that said, let's get started. So here is what we'll be covering in this course. First, we will talk about what is LangChain, why we use it, what problem does it actually solve, and then we will set up our Python environment so that we can actually start using LangChain and start interacting with these APIs, right? So once we have that set up, we are then going to start diving deep into the core components of LangChain. First off, we're going to start working with chat models, meaning we'll basically just interact with OpenAI's chat models, Claude's chat models, all of that in the first section. The second core component of LangChain is going to be prompt templates. Basically, make our prompts to the AI as templates and add placeholders in it so that it can take dynamic values. All right, the next component. It gets really interesting from this point onwards. The third component of LangChain is going to be chains. Okay, so chains in LangChain are like an assembly line. Each step handles a specific task and passes it to the next. Here's a real world example. Okay, so imagine chains like making a coffee, right? First you have to grind it, then brew it, then steam it, and then serve it, right? So that's exactly what we're doing here as well. So if there is a complex workflow, we'll be dividing it into smaller tasks. And once the first task is done, the result of that is passed to the second task. So that is why it's even called LangChain. And even the logo of LangChain has a picture of chains because it links various processes like models, chat models, prompts, databases, calls into a unified workflow. And we have plenty of real world examples for that as well in this course. And then we have RAGs. This is a pretty huge section in this course, and it's one of those important technologies that are helping businesses to increase productivity. So if you've ever heard of custom chatbots trained on a company's private data, the data could be in the form of PDFs or it could be from the database and users can sort of chat with the data, then this is what's going on. RAGs or retrieval augmented generation. And finally, we are going to wrap up this course with another critical component of LangChain, which is called agents and tools. Basically, think of AI agents like a human agent who can see a problem and use various tools to solve that particular problem. It can sort of interact with APIs, send emails automatically, scrape data from a website, run a Python script, or even query a database. I'll give you an example. Imagine an AI agent gets a task to book a meeting. Just like a human, it can check your calendar, it can send an email invite, it can update the CRM as well, all automatically, right? So that is the power of LangChain agents. They can use the right tool for each and every single step. Here is a quick tip. If you want to get a complete overview first, try watching the whole course at 2x speed. Then you can go back and focus on the parts that you actually need most. That's how I learn it because it lets me see the big picture first and see how everything sort of fits together. In the next section, let's talk about what is LangChain, why we even need it. I'm pretty excited and I'll see you there. Alright, so to understand what LangChain is, let's start with a very simple problem. So imagine you want to plan a vacation and you want to seek the help of ChatGPT. So I'm going to say something like, I want to plan a trip to Paris this Saturday. Can you book my flight? Also book a hotel the same day and suggest some good restaurants. Okay, so let's actually see what happens behind the scenes. I'm not pressing enter just yet. So when I press enter, this query is sent to an LLM model. So this ChatGPT application might use a lot of models. It might use ChatGPT 3.5, ChatGPT 4.0, 4.0 mini, a lot of other models, right? So these are the large language models that you see on the right side. The ChatGPT application itself is just an interface for the user like you and me, right? So when I press enter, let's see what happens, right? So you can see that it says, I cannot make bookings directly, but I can help you with planning, right? So this is one of the biggest limitations of large language models. They are smart and can talk about travel, but they cannot actually interact with the real world, right? So on its own, the LLMs are just the brains, right? They can be trained on certain data and it will reason with it, right? But it cannot do anything outside of it. Let's say you want to build an application that needs to have the brains, basically the reasoning ability of an LLM, but at the same time, it also should have the ability to communicate with the real world, right? Communicate with real world APIs, databases, right? Send emails. If you want to do that, we need to have some sort of a framework right in the middle, right? And that is where LangChain comes into the picture. Okay, so LangChain acts as a bridge between the LLMs and the real world. So to put it simply, LangChain is by far the most popular framework that helps build applications using LLMs, right? So in the future, if you want to switch out GPT 4.0 with, let's say, a free Hugging Face LLM, if you're short on cash, let's say, you can easily do so without even touching the code that you wrote with LangChain, right? So with LangChain, the AI that we're working with can do so much more in real world. I'll give you a few examples. So it can access a lot of APIs. For example, it can access flight and restaurant booking APIs from, let's say, booking.com or opentable.com. It can access private company databases to answer customer queries. It can send emails. It can browse Google, Wikipedia. It can scrape websites and a lot more, right? So LangChain doesn't just make the AI smarter, it gives it the ability to act in the real world. This is just a very small example. So as we go through the course, we will explore a lot more use cases. So I hope you're excited. Let's get started. Alright, so let us talk about the prerequisites first. To be able to follow along with this course, you will need Python version 3.8 or higher installed. And the second thing is make sure that you have a code editor installed as well. I will be using VS Code in this course. And last but not least, you will also have to create an OpenAI account because we will be using OpenAI's APIs in this course. If you don't have Python installed, I have attached Python 3 installation tutorial links in the description for both Windows as well as Mac. So once you're done installing, you can come back to this video. And for VS Code, you can go to this particular link right here, and then you can download Visual Studio Code for whichever operating system that you're working with. The installation is also pretty straightforward for this. And finally, let's go ahead and create an OpenAI account if you don't have it already. The reason why we need that is because we need the API key in order to be able to hit that API endpoint to access OpenAI's LLMs, right? So to do that, let's go to platform.openai.com. Okay, so I'm going to log in because I already have an account. If you don't, you can just go ahead and sign up right here. So once you're in, you can click on this dashboard tab right here on your left side. You can see a tab for API keys. So we can click on it. So if you've never created a key before, you might see an empty list right here. So let's actually go ahead and create a new one by clicking on this button. I'm going to name it LangChain tutorial. I'm going to leave the permissions as all, and let's go ahead and create it. All right, so we have it right here. Also, please make sure to save it somewhere in your computer because if you lose it, you will have to create another one again. Okay, and that's it. So far, we have installed Python 3, we've installed Visual Studio Code, as well as we've created an OpenAI account and created an API key as well. So in the next section, let us actually go ahead and set up our development environment using Python so that we can actually start working with LangChain. So I'll see you there. Alright, so in this section, let's actually set up our development environment. So I'm going to create a folder called LangChain. And I'm going to open this folder in my Visual Studio Code. So to do that, you can simply open Visual Studio Code and drag and drop this folder inside of it. And you can see that it's been opened right here, right? So now let us open up the terminal and we have to create something called a virtual environment. So whenever we are installing packages, we don't want it to be available globally. We only want it to be available inside of that one virtual environment. Also, it is a pretty standard process whenever we are working with Python projects. So I'm going to say Python 3. I'm working with Mac, by the way, so I have to say Python 3 right here. But if you're a Windows user, you can just say Python. All right. And then we have to say -m. And this is to tell Python to run a specific module. So -m, and then let's say venv. So this is the module that we want Python to run. And finally, we need to give the name for the virtual environment that we'll be creating as well. So I'm going to name the folder that will be getting created as .venv. So we put this dot here so that the file that will be created will be hidden, but you can also choose not to hide it as well. So in that case, we can just not put the dot there. So let's press enter. And now you can see that we have the virtual environment created. So the first step of creating a virtual environment is done. The next step is to make the terminal point to that virtual environment. Right now, you can see that it is pointed to base, which is the location outside the virtual environment. But we need to point it to the virtual environment because we'll be installing a lot of packages for this course, right? So to change this, VS Code might automatically show a pop-up to accept it right here. But if it doesn't show you, you can just easily click on this button right here and then select the venv directory right here. And that's it. It has been changed to the venv path. So if I open up another terminal window, you can see the venv on the left side. So we are now in the virtual environment. That's it. Our Python development environment is completely set. All right. So now I've gone ahead and created a very simple folder right here and then a file inside of it as well called chat models starter. So inside of it, if I now type, let's say print, let's learn LangChain and hit run right here, you can see that we have the text in the terminal. Right? All right. So our development environment is perfectly done. So we're actually ready to start working with LangChain now. In the next section, we will look at the first most important component of LangChain, which is called chat models. So I'll see you there. So in this section, let us look at the first core component of LangChain, which is called chat models. Okay. So let us now look at the official definition. A chat model in LangChain is a component designed to communicate in a structured way with LLMs. Right? So the LLMs could be GPT-4 LLM, it could be Hugging Face, an open source LLM, it could be Claude Sonnet APIs, right? So chat models in LangChain offer sort of like an interface that you can use to communicate with pretty much any LLM that you want, right? So if I go to the official documentation in LangChain on chat models, you can see that there are different models right here, right? So there is a LangChain chat model for the Anthropic LLM. There is another one for Mistral right here. And since we are going to be communicating with OpenAI's LLMs in this course, then this is the models class that we will be using. And this is the package that we will have to install. You can also see what each and every single model is capable of. We can also use tools using these models. Tools we will talk about in the later part of this course. And then we have the structured output as well, and if the models support JSON outputs or not. All right. So far we know that chat models offer an interface for us to communicate with so many different LLMs APIs, right? But now we need to ask ourselves a question. Why do we need a middleman right here? After all, we can directly call them, right? The answer is yes, of course we can, but as long as we're building smaller apps. But as we start building more and more complicated apps, then you can see it will start getting messy really fast. So here are some advantages of using LangChain model interfaces instead of directly calling LLMs APIs. So knowing these things are important because it gives you a high level overview of why we do certain things. Knowing that, you can architect your own solutions better even after this course, right? So let's look at a few advantages. So reason number one, consistent workflow. LangChain's chat models unify different APIs, saving you from managing each one's unique setup and quirks. We will explore all of this pretty soon. Reason number two, easy switching between LLMs. If you want to switch between one LLM to another, LangChain's chat models make it very simple without a lot of code changes. Reason number three, context management. Working with LangChain's chat models help manage conversation history, letting you keep context across multiple interactions seamlessly. Reason number 4, efficient chaining. You can connect multiple LLM calls and tasks in one structured pipeline, which can be a bit tricky to set up manually. And finally, reason number 5, scalability. As projects grow, LangChain's interface supports more complex workflows, letting you focus on features and not API management. So in this course, we'll be mostly working with OpenAI's APIs. So we will need the chat OpenAI model right here. So if we click on this, you'll find it very easy to understand the documentation on how to set this up. So let us actually go ahead and set up a chat model and start interacting with OpenAI's APIs. So I'll see you in the next section. Hello guys, in this section, let us actually start working with LangChain's chat models. So since we are going to be predominantly working with OpenAI's APIs, I'm going to go ahead and install the chat model related to the OpenAI, right? So if you look at this, this is what we need, right? Chat OpenAI. So if I click on it, and if I scroll down here, you can see that this is the command that we have to use to install this particular package, right? So we have to install this package, LangChain-OpenAI. So let me copy this, come down to my terminal in VS Code, and let me install it. Okay, it's not installing because, yeah, we have to remove this particular percentage sign. All right, now it should install. Let's give it a few seconds. And perfect, it has successfully installed, right? So let's actually go ahead and import this particular chat model in our file. I'm going to say from LangChain OpenAI. So this is the module, and from this module, we want to import the chat OpenAI class. So this is what we need. So we can now go ahead and initialize our model. So we can call this LLM or model or whatever you prefer. So we can say chat OpenAI, and we want to use a certain model, right? So we can pass in this particular keyword parameter, and the model that I want to use for this particular example is going to be GPT-4o, right? And I'm using this particular model because this is kind of the latest model that's been released by OpenAI. And usually the latest models can be a little bit expensive because they are the most advanced model. But if you're a little short on cash, you can always go with GPT 3.5 or GPT 4 even. So now that we have used a chat model to initialize an LLM for us, so this is the variable that we are going to be using to sort of communicate with OpenAI's APIs. So to make an API call to OpenAI, we can just say LLM.invoke. Okay, so we can pass in any string that we want inside of this. Just remember that any time that we want to make any sort of calls to the LLM, just remember that this is going to be the magic keyword that you have to remember, invoke, right? So this is going to be used throughout the rest of the course. In RAGs, it's going to be used in a lot of other sections as well. So just remember that this is going to be the magic keyword, invoke, right? So I can ask pretty much any question that I want right here. So I can say something like, let's say, what is the square root of 49, right? What I'm going to now do is I'm going to store the result of this LLM's response, the API response, inside of this particular variable, and I'm also going to print this result. All right. So now what I'm going to do is I'm going to hit run. Let's see what happens. Okay, so we are getting an error here, and it says that the API key is missing, right? So we have completely forgotten to provide the API key. So let's actually quickly go ahead and create an env file in the parent directory right here. And what should be the name of the API key, right? So what should be the key name, right? So you can see that if I go inside of this particular model, chat OpenAI chat model, if I go inside of here, you can see that it automatically requires this particular OpenAI API key to be available globally, right? So what I can do is I can go inside of the .env file, put this thing here, and I'm going to copy paste my API key that I just copied from OpenAI's dashboard right here. So I'm going to paste this right here. Perfect. Now, if I come back to this file and if I try to run it, we're still going to get the same API key error. And that is because Just because we have created it here does not mean that this file has access to this particular key. Okay, we still have to explicitly provide the sort of access into all the contents of this specifically inside of this particular file. So to do that, we have to install another package. So the name of the package is pip install python -.env. Okay, so it looks like it's been installed. So I'm going to come up here and I'm going to say .env import load.env. Okay, so this is the library and this is what we want to import. This is going to be a method. So to make the contents of the env file available inside of this file, all that we have to do is initialize or basically call this particular method. Okay. All right, perfect. That's pretty much it. So if I now again run this particular file, you can see that we finally get the entire response. So we have the content. It says that the square root of 49 is 7. We've also got additional key arguments. We've also got response metadata and a lot of other things. And just one more thing, if you're not able to see the response down here, in case OpenAI is not letting you access their APIs, it's probably because you don't have enough balance. So if you search in the terminal in the error message, you might probably find that your balance is a little low. So to fix that, it's pretty simple. So just come back to platform.openai.com and then go into settings right here and go into billing, and you can just do a little bit of top up. So the least amount of money that OpenAI accepts is $5. So since we're just learning things, you can just go for the $5. It is probably going to last you a couple of months. So don't worry. So this contains a lot of additional data as to, how much tokens have been consumed and a lot of other data, but we don't really need any of this. We just want this particular content property instead of this entire object. So what I can instead do is I can just say result.content. So anytime that I'm making a call to the LLM, the result that I'm going to be getting is going to have all of this chunk, but the only thing that I'm interested in is the content parameter or the property, right? So let me just clear this out and then run it again for you guys. So you can see that, all right, the square root of 49 is 7. Right? So that is how simple it is to use LangChain's chat models in order to communicate with pretty much any API that you want out there. So right now we're just working with OpenAI's API, and this is basically just an interface that lets us access that particular API. And this is how simple it is. We are just going to provide whichever model that we want to access on OpenAI side. So if we want 3.5, let's say, we can use that as well. If we want 4, we can access that as well. So in this section, we just passed in a very simple prompt to the LLM saying what is the square root of 49. In the next section, I want to send the LLM an entire conversation history. Right? For example, the human said this thing, the AI said this thing, the human said this thing. So basically the entire history is what I want to send to the LLM so that it is able to better give responses because it has the awareness of what happened before, right? So we will see how to do that in the next section. Hello guys, in this section, let us see how we can send past conversation history to the LLM so that it has more context awareness. So to proceed forward, we need to learn about the types of messages in LangChain. So the first one is going to be system message. It defines the AI's role and sets the context for the conversation. It is typically set at the very start of the conversation. So for example, you are a marketing expert. Let's look at the next type of LangChain message, and it's called human message. And this should be pretty self-explanatory. It represents user input or questions directed to the AI. And the last one is going to be AI message. It contains the AI's responses based on previous messages. For example, focus on social media engagement. So now that we know all of the types of messages, let us see how we can use them in our code. So the first thing that I'm going to do is to import all these 3 types of message classes from LangChain. More specifically, we'll be taking them from LangChain core package. And from this module, we extract 3 classes. First is system message, and then the human message, and then the AI message. So first, let's sort of hard code a conversation history so that we can send it to the LLM. To do that, we can initialize a list called messages, and the first item should be the system message. Remember, the system message is what defines an AI's role. right? So I can say you are an expert in, let's say, social media marketing or social media content strategy. Now I can provide the human message or the question that I want to ask. So I can use the human message class from up here and provide in the content. So I can say, give a short tip to create engaging posts on Instagram, because I don't want it to go off and give me paragraphs upon paragraphs, right? Perfect. We have a simple conversation list. We can also add a lot more to this, like add another AI message and then another human message. But for now, let's just run it. Now we need to talk to the LLM and get an answer. So we can follow the same thing that we did earlier. Let me copy paste this from the starter file. And now instead of this particular string, we are now going to pass in this list of messages. So let's remove this and put the messages list here. So this invoke method is pretty versatile, as you can start to see, right? Because we can pass in strings, we can pass in this list as well, and LangChain knows exactly what needs to be done. It sort of abstracts away all the complexity so that it gives you a very clean interface to work with, right? So let's also print the content from the result as well, right? Now let's open the terminal, clear all of this, and let's run the file. So now you can see that the LLM returns our data, our answer. So it says to create engaging posts on Instagram, focus on storytelling by using captivating image or video paired with a concise, relatable caption, right? So it is keeping it very concise as well, right? It is giving us a short tip. So this is basically how you can, you're sending the system message and the human message. And we can also take this a next step as well. So basically we can copy this entire content and then put it inside of a AI message right here. And then again, add another human message on top of it. Okay, so I know that this seems a little weird because we're statically sort of like we're hard coding all of the data, but knowing how these things work is crucial because we can then later make it dynamic. All right. So what we learned just now in this section, where we pass in the entire past conversations to the LLM, is pretty important, especially if you're building real world applications, because if you're building a real world production grade application and users are talking to the AI, the user also expects the AI to remember the past conversation, right? So that is exactly what this lets us do. So we need to know how to program these things in the backend, and having it in a list using these three types of messages, the system, human, and AI, this is pretty important. So I hope that you're starting to see how it is all coming together. So far we've only been interacting with OpenAI's LLMs, right? In the next section, let us also look at, how we can easily sort of switch between different models using LangChain. So I'll see you there. Welcome to the third example of LangChain. We are going to see how easy it is to switch between different models using LangChain. So far, we've only been working with OpenAI's chat models, right? So I have gone ahead and written out some code for you. So this first part of the code, you should be familiar already. We have the messages list. We have a simple system message and a human message. And for this, we are using the OpenAI chat model. But in the future, if you want to switch to a different model, and this could be for whatever reason, maybe this model is a little more pricier, or there is another model that is doing a certain task much better or faster even, right? Whatever is the case, you can sort of easily switch models in LangChain. So in this section, we will look at using Google's Gemini model as well as the Anthropic model, which is Claude's. All right. So you can see that up top, I have installed two more chat models to communicate with Google as well as Anthropic. So if I scroll down, you can see that the process is no different to OpenAI's. So we just use a different model. So in this case, we are using Chat Anthropic, and we're passing in the exact model inside of Anthropic that we want to work with. So in this case, this is the model that I want to work with. All right. No different to working with, let's say, how we were doing so far with OpenAI's chat model, right? Same thing for Google Gemini as well. So if you have any questions, or if you want to download the right chat model package, I've provided the link to the LangChain docs where you can find the right model that you want. So if I scroll down even below, you can see that I have used LangChain's chat model for Gemini, and all that I'm doing is specifying the exact model that I want to use. So in this case, we are using Gemini 1.5 Flash. All right. So as you can see, LangChain abstracts away all of the complexity to sort of interact with different models APIs. And also it makes the process very consistent as well, right? So I have attached all of the docs related to what are the models that are available in Gemini, what are the models that are available in Claude, etc., etc. So knowing how to switch between models can be pretty handy, because let's say you're working on a product or you're building a solution, and based on the task at hand, maybe a different model is better at handling a certain thing. Maybe another model is faster. Maybe another model is more accurate. Maybe another model is more faster or cheaper, right? So LangChain also lets it very easy to sort of help you switch things up as well. All right, guys, that's pretty much it for the section. In the next section, we are going to be doing something very interesting. We're basically going to be having a conversation with an LLM through our terminal. Very similar to how ChatGPT works, but you're going to be doing all of this locally instead of your terminal. So I'm really looking forward to it, and I'll see you there. Hello guys, welcome to the fourth example in chat models, where we're going to have a real-time conversation with a chat model through our terminal, right? So it's going to be very similar to what we do in ChatGPT application itself, but instead we are going to do it locally on our computer. So as you can see, I've already prepared the code. Let me show you the result of it, and then we can jump into the code. So when I hit run, you can see that it says you, right? It is basically prompting me, the user, to give it a question, right? So if I were to say, let's say, what is the square root of 49? And when I press enter, let's wait for a while. And now you can see the AI's message saying 7, right? And now I can also ask a follow-up question, something like, how did you get that value, right? And so I can say, how did you get that value? And then press enter. And you can see it is walking us through the reasoning, right? It's great because it sort of remembers the previous conversations, basically the history or the context of the conversation. So now if I wanted to, let's say, know the square root of 81, right? So I don't even have to explicitly type out what is the square root of 81. I don't have to do that anymore because it remembers, right? So I can just say, do the same for 81 and press enter. Let's wait for a second. So you see, it already knows that we're asking for the square root. So it is already giving us the value, which is 9, right? And now if I want to exit out of a terminal, I can just say exit, press enter, and now we're out of it. So basically how ChatGPT works under the hood, let's actually see how we can implement this in the code. So as usual, as we've done in the previous sections, we are initializing our model right here, and then we are loading all the environment variables. Now this is where it starts to get interesting. So very similar to the list that we had 2 sections ago, we're still going to work with a list here. The list is going to have AI messages, system message, human messages, right? But this time we're not going to have it hard coded. Instead, we're going to be adding things dynamically, right? So to start off, we have an empty list here called chat history. So as we discussed in the previous sections, the first item of the history array or the list should typically always be the system message. That sort of gives AI a certain role or a responsibility, right? So we've created a system message right here, and then we've added it to the chat history list. So in this case, it's going to be a helpful assistant. I'm keeping it very simple. So let's move on. So right here we have a while loop that keeps on looping until a certain condition is met, right? So let's go through it line by line. Let's see what's happening. So to start off, we are basically prompting the user, which is me or the user basically, to type in a string. It could be a question, it could be anything, right? So I want to ask AI a question right here, like we did in the demo. What is the square root of 49, right? So the entire string of what is the square root of 49 is going to be in this query variable. So in case we put the string exit, then we're just going to break out of this loop, but we are not going to do that. So it's going to come to this particular line. So this line adds the human input message to the list as the human message. Very simple, right? Now, as soon as the list has a human question at the very end, we're going to send the entire list with all of its history to the LLM. Now, whatever response that we get back from the LLM is going to be the AI message, right? So the response, which is now the AI message, is then put into the list right here. And the while loop just keeps on looping. So that is how simple it is to communicate with an LLM through our terminal, right? So all the code, again, if you get stuck anywhere, all the code is available in the repository. So do pull it and do run it by yourself. All right. So in this section, basically we've seen how to store all the conversation history in a local variable that is kept in memory, and that is the chat history variable, right? But in real production applications, normally you would save all of the conversations in the cloud, so that even if you exit out of the terminal in this case, or even if the user were to close the application, the data is still going to remain in the cloud. So let's actually see how to do that in the next section. Welcome to the last example in chat model section. So far we've been storing all the past conversations in a variable in memory, right? But in production grade applications, we might ideally want to put it in the cloud so that the user can sort of log back out and then come back after a week and still continue the conversation, right? So we're going to be doing that in this section. So all the history is going to be retrieved from the cloud as soon as the application is going to be turned up, basically. So for that, we're going to be using the Firebase Firestore database, right? So let me show you a quick demo of what we are going to be doing in this section. So I'm going to run this file. So we have a message prompting the user to type in something. So I'm going to say, let's say, hey, how's it going, right? It's very simple. Before I press enter, let's actually go to the Firestore. And you can see the database currently is empty, right? So let's come back. So if I come back and if I press enter, you can see that the AI responds with a very simple message, right? Now I'm going to ask it something like, let's say, what is 2 plus 2? Enter. Let's give it a few seconds. Yeah, it gives back 4, right? Now, if I go back to the database, you can now see that we have 4 messages that have been added, right? So now if I stop the terminal, so let's actually do that. Let's stop the terminal and then run the file again. Okay, you can see that all the messages are retrieved from the database so that the conversation actually continues, right? So that is what I've coded out already. Let's quickly walk through it and you'll find it to be pretty simple, right? The actual main code is not really that much different to what we wrote in the previous section. Most of the difference is just in the Firebase setup part. Okay, so to make it very, very simple for you, I've typed out installation steps right here. It's very straightforward. So once we do the cloud setup works, Firebase, Firestore setup works, the rest of the code is pretty much the same. There is literally no difference actually. So let's see. So the first thing that we're going to be doing is creating a Firebase account. So you can just go to firebase.google.com. Okay. And then let's go to console, right? So click on this go to console. And then we are going to enter the name of the project. So I'm going to call it LangChain. All right. So we don't really need analytics for this. And the project creation itself might take a minute or so. Let's actually give it some time. All right. So it's done. And let's click on this button right here and you are in the project now. Now you can just go to the build drop down on the left side and choose Firebase database. And this is what we're going to be working with. Okay. So just go ahead and click on create a database. I'm going to leave the location as it is. I'm going to click on next, next. And now we can leave it in test mode because the application is not live yet. And once we click on create, Firestore will be set up for you in this project. So if you haven't worked with Firestore before, it is basically just a document based NoSQL database. So you have something called a collection. In this panel, you can have as many collections as you want. So for example, we can have a collection called users, and each user document can in turn have a collection inside of it. Let's say user messages, right? And each of those messages inside of the user messages is going to be what? You guessed it right. It's going to be a document. So it sort of alternates. So we have collection, document, right? So just a short crash course on Firebase Firestore for you. So let's head back and let's look at the third step in the list. The third step is going to be, you need to retrieve the project ID of the project that you've just created. So you see, our application needs to know which project's Firebase database it needs to make changes to, because we can have multiple Firebase projects, right? So to get it, we can just go back to Firebase, click on this gear icon, project settings, project ID. So we have it right here. So I'm just going to copy this, come back here, and I'm going to replace this value. Perfect. Now let us look at the fourth step right here. It might look a little bit complicated, but it's actually very simple. So all that we're doing is we need to install the Google Cloud CLI in our computer and sort of authenticate ourselves so that Google or Firebase sort of trusts us when we make changes to the database, right? So the setup is extremely simple. Just click on this particular link right here, scroll all the way down. If you're a Mac user, just download the right package based on your operating system. The same for Windows as well. And then wherever this particular package is installed, probably it is going to be in the downloads folder. So just go to that particular path in your terminal and run this particular command. The same thing for Windows as well. All the instructions are easily laid out here. You just need to follow it, right? And finally, initialize the CLI by running this last command. And that is it for this step. Let's look at the next step. So we have to configure something called the ADC, right? The documentation makes it very, very easy to set this up. So let's click on this particular link and let's scroll down, and you will have to run this particular command and do an application default login, right? So we have to do that. And finally, you will have to run this command as well. And that is the last step. It is pretty simple. There's tons of tutorials out there that will help you set this up. And to be honest, you don't even need any of these tutorials because the documentation is pretty straightforward as well. But we're not going to go too deep into it in this course because it's a little out of scope for this course, right? And finally, we're going to install this particular package as well. Again, this package is built by LangChain and it does all the magic to communicate with the Firebase Firestore, right? So this entire thing, the Google Cloud setup, is kind of the most difficult part of the section, the setup of it, but the rest of it is very similar to what we did in the previous section. And at the end, we just have to make sure that we have all the right imports up here. Perfect. So let's actually scroll down and see what we have. So the first thing is we need to initialize our Firestore client. So we're going to pass in this particular project ID as well that we had just copied a while ago, right? Now we're going to initialize the Firestore chat message history. This takes in 3 arguments: the session ID, which is going to be the unique identifier for the current chat session. So we can name it pretty much anything that we want. I've just gone ahead and named it user session. But ideally, this should be a long 16-digit string, right? Because there's going to be a lot of user sessions. And then we are going to have the collection name, right? So the collection name that is going to be created and updated in the Firestore is going to be chat_history right here. And you can name it message history as well, right? Pretty much anything that you want. And finally, we are going to pass in the client as well. So the rest of the code is literally no different to what we did in the previous section. So the only change that we're going to be doing is instead of having the history list in memory, we are now going to be having it from the cloud, right? So this chat history is being returned by the LangChain's Firestore class. So now if I run this file, we can just start chatting with the AI, right? And more importantly, we get to store every single message in the cloud. And this particular class, the Firestore chat message history class, sort of abstracts away a lot of the complexities. So it sort of enables very smooth communication between LangChain as well as the Firestore, right? And that brings us to the conclusion of chat models. So I hope you now have a pretty good understanding of how chat models work and how you can actually build production grade applications by storing your messages in the cloud. And also, I'm pretty excited about the next core component of LangChain, which is going to be prompt templates. And it's one of the most easiest components to learn. But at the same time, when you're building production grade applications, that would save you a lot of time. So I'm pretty excited and I'll see you there. Welcome to the second core component of LangChain called prompt templates. This is something that you will find it very easy to understand, but in production grade applications, you'll find yourself using this a lot. So let's actually go ahead. Let us look at an example and you'll be able to grasp it very quickly. So this is an example of a prompt. So we have write a tone email to company expressing interest in the position, mentioning the skill as the key strength. So all these placeholder values can be replaced with custom values, like the tone could be write an enthusiastic email, write a confident email, write a professional email, write a warm email, right? So the company here could be pretty much any company, right? It could be Google, Amazon, Samsung, whatever. And the position here could be, designer, developer, etc. And we have the skill as well, right? So if we pass in these values as input to the prompt, with, let's say, tone as professional, the company as Samsung, the position as AI engineer, we get a string like this with the values replaced. That is it, right? So if you're building a product that generates emails based on all these varying parameters, then you can imagine we can easily make it happen with prompt templates. So let's actually quickly see how we can implement all of this in our code. So you can see I've created a new file under prompt templates and I've initialized a chat model here as well. So it's no different to what we've been doing so far. So now is when we are going to start working with prompt templates. So step one, we create a string with the placeholders. Also note that this string right here is only a prompt that you and I can understand. So this is the first step, right? So the next step is to convert this prompt into a format that LangChain understands. So that is going to be step two. So to do that, I'm going to import something right here. So I'm going to say from LangChain core dot prompts. So from this particular LangChain core package, we need the prompts module. And from this module, we want to import the chat prompt template class. So if you're curious about where we got this LangChain core from, because we never installed it, right? It automatically gets installed when we install the OpenAI chat model package that we installed earlier in the first section. All right. So to check, you can just go to the virtual environment folder inside of the library right here. You'll be able to find the core inside. Okay, it's right here. All right. Now let's look at step two. So let's actually go below the template string right here. And let's convert this prompt into a prompt that LangChain understands. So I'm going to name it prompt template, right? Equals chat prompt template. And we want to use the from template method. And we want to pass in the template string right here. So if I now go ahead and print this variable and hit run, you can now see an object with various properties like what the input variables are and a lot of other things, right? Great. So this brings us to step number 3. Let's populate the placeholders with actual values. So to do that, I'm going to say prompt template and I'm going to use the magic keyword invoke to tell LangChain to do that. In the last section, we used the invoke keyword to talk to the LLM. In this case, we are going to do it to replace all the placeholders. So this takes in an object, okay? So I'm going to copy paste an object right here. And I'm going to save the returned value into a variable called prompt. Okay, so let's print this as well. Hit run. And now you can see LangChain has converted this prompt template into a list with human message. Because only a human can prompt, right? Pretty obvious. Also, if you remember from the previous sections, this is the exact structure that we sent to the LLM for answers with the list and everything, right? We can do the same thing here. We can say LLM dot invoke and pass in the prompt. And then we can store the result in a variable called result. And let's print that as well. So just the content. All right. So if I hit run, let's give it a few seconds. And now you can see the subject and the content of the email and everything right here. And the tone that we provided was energetic. So the tone of the email will also be energetic, right? Perfect. So far we've been able to take a prompt and make it into a template and send it to an LLM. But there is one limitation with this particular approach. So when we convert our Python string prompt, right, into the prompt that LangChain understands, which we do right here, you always see it creates a list with just one human message, right? But what if we want more control, right? What if we want something like this, where the system message is also customizable? And that is what, let's say, your product, the product that you're building needs, right? So doing that is very simple as well. So I'm just going to paste a bit of code here and let's go through it step by step. All right. So we're going to have a list of tuples, right? So a tuple is a data structure in Python and each tuple will have the type of message and the message itself. All right. So in this example, we have the system message and the human message with placeholders. All right. Now, this is a template that you, me, Python can understand, but LangChain does not understand it, right? So we're converting that right here. So as you can see, this from messages method not only takes a simple string, but also a list of tuples as well, right? And then finally, we're replacing the values by passing in these placeholder values and invoking it. Now I've already gone ahead and printed it as well. So let's actually run this file right now. All right. So now you can see we have an entire list with system message as the first item, and the placeholder value has been replaced here as well. Plus, we also have the human message as well. Now, this could be a functionality that your product requires, and now you know how to do it. Now we can easily pass this fully built prompt and get responses from the LLM by using the LLM variable that we've just created using the chat model and passing this final prompt. Okay, and that is it for this section. As I said, this is a relatively very simple component of LangChain, and that brings us to the end of the section. In the next section, we are going to be looking at another core component of LangChain called chains. And personally, it is my favorite because it is really fun to work with. At the same time, its potential is really unlimited. So I'll see you there. In this section, we are going to be covering the third component of LangChain called chains. And it is personally my favorite component of LangChain because it lets you connect multiple tasks together by chaining it together, and it helps you create sort of like a unified workflow. Let's look at a quick example. So if you remember from the prompt template example, where we just created a prompt template called the invoke method on it with the placeholder values passed in, and it gave us the final output, right? So this can be considered as one task. Another task could be passing that prompt to the model and calling the invoke method on it again. So we can chain the first task and the second task so that once the first task is done, the result of that is passed to the second task, and then so on and so forth, right? So you can think of a third task as well, right? So from the second task, we're actually getting the response from the LLM. So what we can do is there might be a requirement in the product where you might have to convert that particular response from the LLM into a specific language, let's say French, right? So that could be a third task. So sending that message to the LLM, saying it, okay, convert this particular message into French and then send it to me. So that could be the third task. A fourth task could be sending that particular response, the French response, to another person via email, right? So that could be a fourth task. So we're chaining all of these tasks together to create a unified workflow. So that is the idea, right? So by using chains, we can do pretty much anything that the business or the product requires just by connecting it with something called chains. Next, we're going to be looking at all the possible ways to chain tasks. So the first task is the extended or sequential chaining, right? So this is basically what we've been discussing so far, right? We have the first task, the response of that is getting sent to the second one, and then the third one and the fourth one. So it is in a straight line, it is sequential, right? So that is called extended or sequential chaining. The next type is we have parallel chaining, right? So with this type of chaining, we can run tasks parallelly or simultaneously without it being dependent on each other, right? So in the previous example, each task was sort of dependent on the previous one, right? But here it doesn't have to be dependent. I'll give you an example, all right? So here's an example. Task 1 could be brewing a cup of coffee. Task 2 could be making a bread toast. Task 3 could be frying an egg, right? All these tasks run parallelly and quickly and then sort of converge into the fourth task, which is to serve a breakfast plate with the coffee, toast, and fried egg. So in this example, you can see that none of these tasks are dependent on the previous one. They all execute parallelly and then they converge, right? So that is what is called parallel chaining. And finally, we also have conditional chaining, which can be used in certain scenarios. Here, we start a task, and based on the result of the task or the condition, it can either go here or here or here. In parallel chaining, all the tasks execute simultaneously, all the chains execute simultaneously. But in this case, based on a condition, it will only go towards one chain, right? I'll give you an example. So let's say in a customer support chatbot, if the user selects technical issue, the bot runs a troubleshooting sequence, which can be thought of as the first branch. If the user were to select billing question, it triggers a billing inquiry sequence, which is the second branch. Whereas if it is a general question, then another sequence, it could be an FAQ sequence, right? So based on the condition, based on whatever the user selects, that particular chain, the flow goes into that particular chain. All the chains do not execute, right? So I hope this high level explanation is sufficient. Let us actually jump into our code and see how to implement all of this using our code in the next few sections. I'll see you there. Hello guys, welcome to the first example in chains for LangChain. So as you can see, I've already prepared the code here as well. So let's walk through this step by step. All right. So the first section is very similar to what we did in the previous sections. So all that we've done here is we've initialized our OpenAI chat model, and then we're also creating a prompt templates, basically creating prompt templates using a list of tuples. Right? So this is another method that we saw, right? Also, we know that we're doing it this way because we want to include a lot more information inside of the template, right? So we want to include the system message, AI message, human message. So that is why we're doing the tuples way, right? We also have a system message here saying, you are a facts expert who knows facts about any animal, right? It could be cats, dogs, elephants, right? And the human message is saying, tell me it count, right? It could be 2, 3, 4, 5, any number of facts. So here is the first task that I want to do. First off, I want to populate all these placeholders and create the final prompt, and then pass that prompt to the model as well, to the LLM as well, right? So what did we do earlier in the first few sections? We basically did invoke on the prompt template, and then again we did an invoke on the model. So it was a separate, the tasks were separate, right? It is the same sequence, but we had to repeat a few things, right? But using chains though, we can do it very easy without saying invoke every single time. So we say prompt template, which is going to be the first task. And then we use the pipe operator that is going to be the chain for us. Very, very simple. Just the pipe operator is going to connect different tasks together. So once this particular task is done, we pass the result to the next task, which is the model. Now, when the response comes back from the LLM, it is then passed into another task, which is basically just a function called string output parser. So what is it going to do? It is just going to extract the content property alone from the whole object. You know that, the response of the LLM is going to be, it's going to have a lot of properties, right, in that object. This function is just going to extract the content property. That is it. So you can see I'm using this method from here, up here, right? You can also do the same. You know what? Let me just remove this for now and show you the output first. Next, how do we invoke this entire chain? We say chain dot invoke, and then we pass the object with values that the prompt template needs. The prompt template requires a lot of these placeholders, right? We are passing all of that here. So whatever we pass in here will be available across the chain. So if we have another prompt template here as the fourth task, let's say, we can pass in a third or the fourth property in this object as well, right? So whatever we pass in here, it will be available across the chain. So even if there is like a 15th or the 20th task is going to be a prompt template, whatever we pass in here is going to be available there as well, right? So let us now quickly run this file, right? And and perfect. We asked for just 2 facts and we got just that. But along with that, we also have a lot of other stuff as well, right? Which is why we need to add the string output parser task or the method, right? And what this is going to do is, this is going to select only the content property from the response from the previous task. The response from the previous task was the response from the LLM. All right. So if I change something here also, like let's say change the animal to, let's say, elephant, and make the count to 1, right? And run the file, right? Let's give it some time. Right, perfect. So we get exactly 1 fact about elephant. So I hope that you're starting to see the power of chains and how simple it makes the code look and how readable it looks, right? Compare it to the previous sections where we did it step by step, separate, right? So let me actually put this side by side so that you can actually see how much less code that we had to write this time. So with chains right here, we chained a prompt template and then sent that to the LLM and then printed that with just a few lines, right? Whereas without chains on this side, there were a lot of additional steps that we had to do, right? So this is the difference. Chains simplify a lot of things, right? So in the next section, let us see how chains sort of work under the hood so that, I'd be able to write my own tasks, like custom tasks. So for example, right here, we used a pre-built method that only extracts the content property, right? But what if I want to write my own method that, I can configure it to do pretty much anything that I want, and I can chain that as well, right? So to do that, we need to understand how chains work under the hood, and that is exactly what we're going to be seeing in the next section. Hello guys, welcome to the second example in chains where we are going to be seeing what is going on internally in a chain. So basically if we understand that it will make it easier for us to customize it based on our own use case, right? Our own business necessities, right? So in the previous section, we essentially connected different tasks together using the pipe operator, right? So what did we do? We created a prompt template, right? And the result of that is passed to the model, and then the result of the LLM is then passed to this other task which only extracts the content property, right? So for this section though, let us actually try to implement the same thing but without the pipe operator, right? That will help us see what is actually going on under chains, under the hood basically, right? So what I've done is I've just gone ahead and created another file right here, and I've created the code here as well, right? So if we scroll down up until here, it is all the code that we'd written in the previous section, no different, okay? So we're creating the model, and then we're creating the prompt template, and then we have all the placeholders here as well. Now we basically know the goal, right? We know we need to create a workflow that takes the prompt template, invokes it with all the values, and then creates the final prompt, right? So that is going to be task one. And the result of the task one, the chat model should take that and make a call to the LLM, right? So that is going to be task two. So this is what we know. And finally, the task three is to basically extract the content property alone, right? So we are going to be chaining all of these tasks together with something called a runnable lambda, okay? So if we scroll up to the very top, we can see that we're importing something called runnable lambda and something called runnable sequence from LangChain. So this is very important. This is what we're going to be learning in this section. So what is it actually, right? So to put it very simply, a runnable lambda is just a simple wrapper that lets us create each task as a single reusable unit. Each runnable lambda takes an input, does something with it. It could be like filling in a prompt or calling the model, and then gives us the output. So this way we can connect each step smoothly, okay? So we have the first runnable lambda, which is going to format the prompt. And inside of the runnable lambda, we are providing a function which takes input values and returns a computed value, all right? So in this case, I'm using something called a Python lambda function. But you can use pretty much any, you can use even regular functions if you want. Basically just a function that takes in an input and then returns an output, right? So if you do not know what Python lambda functions are, it's basically just a function that you can write inline without even a function name, right? It's just a very simple empty function that takes in something and then returns something. So if you want to learn more about it, there's tons of tutorials out there. But yeah, so this X is the input to the lambda function, and this expression is going to return the output, right? So as you can see, this object or the dictionary is what will be passed in as X inside of here. And then we are going to format the prompt by spreading out this object as multiple arguments. Okay, and this format prompt method is going to replace all of the placeholder values with the passed in values. Note that we are not calling the invoke method here as we did in the previous sections. So there is a small difference, okay? So invoke method, basically what it does is it not only replaces the placeholder values, but it also converts the data into the right format that can be sent to the LLM, right? Whereas this method only replaces the placeholder values. The process of converting the data into the right structure that can be sent to the LLM, all of that will be done down here when we invoke the chain, okay, not up here. So this constitutes as the first task or the first runnable, right? In LangChain, we can think of each task as a runnable, okay? We can call each task as a runnable as well. Let's now look at the second task. So the second task is to take in a prompt string from the previous task, that is, and then call the LLM using the invoke method. And we know that the last task is to only extract the content keyword from the response of the previous task. Okay. So far we have a total of 3 different tasks, or we can also call them 3 different runnables, but they're all separate, right? They don't actually work with each other as a single unified workflow, right? So the next step is we need to chain it together, right? So this is where LangChain provides something called a runnable sequence. So if you remember, we imported it, right? Runnable sequence. So using this particular class, we can chain multiple runnables together. Okay. So you can see this is what's going to return us a chain. And always remember, this particular runnable sequence class is always going to take in 3 parameters. Okay. So it is always going to have the first middle, and the last parameters. The first task is always going to have the first task. It's pretty intuitive, right? And the last one is always going to have the last task. And in the middle, it does not matter if you have one task, two tasks, 5, 10, 100 tasks. All of those tasks needs to be put in this array format in the middle parameter. Okay, so why do we do it like that? Well, if I go inside of this class by pressing on the command on Mac or control on PC, and then I'm going to scroll down to the class definition, you can see that the first and the last is going to be one runnable each, right? So the first parameter and the last parameter is always going to take just one runnable, and the middle one is going to be a list of runnables, right? And also if we scroll up a little bit, you can see that it says a runnable sequence can be instantiated directly, or a more common way to do it is by using the pipe operator. So coming back in your projects, we can either use this particular class and chain runnables together, or you can use the LangChain expression language. So LangChain expression language is basically using the piping operator, the pipe operator, and connecting different runnables together. Okay, so we can also do it like this. Under the hood, both are the same, right? So you can create your separate runnables using this runnable class and pass in a function, a normal Python function or a simple Lambda function. It needs to take in this X amount of inputs, and it does something inside of it, and then it returns a value. Okay, so once you have the runnables, you can chain it together using the one way or the other. We can either do it by piping it together using the pipe operator, or we can use this particular class. So when we put it all together, we are finally going to get our chain. Okay, and we can invoke it by providing all of these placeholder values. So now I'm going to run our chain. So I can either click on this play button right here, or you can just go to your terminal and say Python 3 or Python if you're a Windows user, and then just go to this file and then hit enter, right? So I'm going to click on play. Let's give it a few seconds. And perfect. There we go. So we have 2 facts about cats, because that is exactly what we specified here, right? So that is how things work under the hood. Personally, I prefer to work with the pipe operator, basically use the LangChain expression language, but you can also use this particular class. You know what? Let me actually put it side by side so that you can actually see the difference. Okay. So you can see that compared to doing it this way, using the pipe operator is much more easier to understand, right? Yeah. And in the next section, we are going to be looking into something very interesting. So if you remember from the overview section, we saw that there are different ways of chaining chains, right? So for example, we had extended chains, we had parallel chains, branching chains, conditional chains, right? So we'll actually look at examples for each of those types and see how real world applications are built, so that you get a clear idea of where we can actually use it, right? So I'm pretty excited, and I'll see you there. So in this section, we'll see how we can actually extend the chains that we have written so far, and how we can continually add on more and more runnables. So I've already populated the code, as you can see right here. We are working with the same prompt as the previous section, but I've just given it a slightly better name. I've also added a few more prompts here, but actually let's just go to the chain itself right here and see what we're doing. We'll take it from the ground up. Okay. So the first 3 runnables we've already done, right? So basically we're just going to, we just have the first prompt, which is going to tell the model to generate a certain number of facts about a certain animal, right? So in this case, 2 facts about cats. And we're extracting the content alone right here. Okay, great. So now we have 2 facts. So what next? So let's say, based on my use case, I run a French Twitter page and actually not an English Twitter page, right? But the response that we would have gotten from the model is going to be in English, right? So now the next thing that I want to do is send that text to an LLM and ask the LLM to convert it into French. Okay. So to hit that LLM, what do we want to do before that? We want to always do one thing, right? We need a prompt template that is going to tell the LLM to translate it to a certain language, right? So what input does the prompt template require? It requires an object like this to be passed into it, right? A prompt template always requires an object that needs to be passed into it, right? But is the result of this string output parser an object? Of course not, right? It only has the content string, right? So we need to prepare the input so that we can actually prepare the prepare to pass it inside of the prompt template, right? So what we've done here is that we have written a runnable called prepare for translation that takes the output of the previous task. And then you can see it also provides the output as well as the language, and then returns it as an object to the next task, right? So now that object goes inside of the prompt template. Okay, it says that you're a translator and your job is to convert the text to a certain language. So we have provided the text as well as the language in the object. Now the final prompt will be generated as well, right? So now that the prompt is now sent to the model, which now gets invoked, and we finally get the content printed to the console, right? So that is how simple it is. Let's actually run this file. So I'm just going to go ahead and click on the run button. All right, we can see that it is starting to execute. Let's give it a couple of seconds, and perfect. So you can see that we have 2 facts about cats in French. I can't read it either. And we can even further extend this, right? So we can create another runnable, which is now going to talk to the Twitter API, right? And then post that particular fact as a Twitter post, basically, right? So you can see that sky is the limit when it comes to working with chains, right? We can keep on adding more and more chains sequentially in a straight line, right? So that is what sequential chaining is in a nutshell. So in the next section, we'll actually be looking at a type of chaining called parallel chaining. So I'll see you there. In this section, let us see how we can use parallel chaining in LangChain. And just to jog your memory, let's actually go back to the diagram. So what we're going to be doing is, so first off, we are going to kick off one task, okay? And that triggers 2 different chains, or 3, or even 100 even, right? And all those chains run parallelly at the same time. And once all of those chains resolve and come to an end, we can then do something with the result of all of those chains, right? So I'm going to be using a very simple example right here. Let's say I want to write a blog post about a movie that I'm critiquing or analyzing, okay, a blog post. So let's say the movie is Inception. And I want the first section of the blog post to have my analysis of the plot, okay? And I want the second section of the blog post to have the analysis of the characters involved. So the first section is going to be all about the plot, and the second section is going to be all about the characters, okay? So what can we do first? We can first get the summary of the movie from the LLM, and once we have it, we can actually start off 2 separate chains, okay? So the first chain is going to analyze the plot, and the second chain is going to analyze the characters. Again, it's a very simple example, but you can imagine that we can apply it to pretty much anything. Basically, we trigger one task, and that is going to set off several chains parallelly. And then once all of it comes to an end, we do something with the results of all of those, right? And that's exactly what we're doing here as well. So let's actually go down to the chain itself. You can see I've already prepared the code, and let's actually go through it one by one. So as we discussed, we are first getting the summary of the movie from the LLM. And to get it from the LLM, we need to prompt it first. Okay, so just always remember that right before calling the LLM, always prompt it, because it makes life so much easier for us. So we have a summary template. If I go ahead and click on it with command, the system message says, you are a movie critic, right? Provide me a brief summary of the movie. So we're passing the movie name down here when we're invoking this chain. Okay, now this is when it starts to get interesting. So once we get the content alone, we are now going to start something called a runnable parallel. Okay, so basically this is a class that LangChain provides that will help us run multiple chains simultaneously. So we are basically, you can see that we are importing this from up here. So let's come down, and you can see that we specify a branches directory, and we can actually provide a name for each of the branches or the chains that we want to start. Okay, so in this case, we have the plot chain, which is going to analyze the plot. And then we also have the characters chain, which is also going to analyze the characters, right? Okay, you picture this, right? We have the first chain and the second chain, and we're basically naming it right here. So let's look at the first chain. I'm going to click on it, and you can see that this is a chain itself, right? So the summary of the movie from the previous task, you remember the first task was to gather all of the summary from the LLM, right? So that summary of the movie from the previous task is passed into this first runnable lambda task, okay? So here we're constructing another prompt. So here we are just creating a prompt that tells the model to analyze the plot. If I scroll up here, you can see that it says you are a movie critic, and we provide in the plot here as well. Okay, so we are passing it over to the model now, and finally we are going to get the output right here. Okay, so this is the exact same thing that we're doing for the character analysis as well, right? So we're going to create a prompt, passing in the plot summary, same as before, making the LLM call and keeping the character analysis result ready. Okay, so once both of these chains we have both these chains, right? So once both of these chains are done with their execution, you can imagine that both of those chains are running parallelly, right? One can end earlier, one can end a lot before, but basically once all the parallel chains are done with their execution, we get to the next stage in the chain where we have a method to combine all of the results, right? So you can see the result of the runnable parallel is an object, and the object is going to have a property called branches, and each of the branch names with their corresponding result will be present inside of that as well. So if we actually take a look inside of this method, that is all that we're doing right here, right? All that we're doing is combining it all together. That's it. So let's run this file and then see the result. And it's going to take a while because it's first generating the summary, and then another API call goes, and then it starts two different chains, right? One chain is for the character analysis and the second chain is for plot analysis, right? All right. So we have the result right here. We first see the plot analysis, and if we scroll down here, we can see that we have the character analysis as well, right? So this is just a very simple example. You can use this for a variety of use cases based on the business requirements, right? So I'll also give you another example so that you can see where we can apply this concept of parallel chaining, right? Let's say you want to write a social media post on multiple channels, okay, on the same topic, let's say, right? So we have Twitter, we have LinkedIn, Instagram, Facebook, right? All of these channels have different formats, right? We have to write our content in a different way, right? We can also generate a full-length YouTube script as well, right? So what could be the first task that we have to do? The first task is to basically collect all of the information on the topic, right? So let's say that's what we first do. And once we have that, we can then set off a chain for each and every single social media channel, right? So because each and every single channel have their own style of content, right? So we can also have each chain talk to the APIs of each of those channels and also post them for you, right? So we collect all the necessary information. We set off multiple chains parallelly to execute. They all do their own separate things where they are formatting the content based on the channel that they are focusing on, and then they also communicate in the next runnable. They also communicate with the corresponding channels APIs and post them. If you don't want LangChain to directly post that particular post, we can actually talk to the draft APIs, right? That's basically just going to create a draft in that particular platform, and then we can just review it, right? So basically the sky is the limit, right? And that is it for parallel chaining. I hope that you understood how we can actually use parallel chaining to apply for real world use cases. So in the next section, we are going to be looking at the last type of chaining, which is called conditional chaining. So I'll see you there. So in this section, we are going to be looking at the last most commonly used type of chaining called conditional chaining, right? So as you can see, I've already prepared the code for that. But before we jump into the code, it will help if we sort of understand the problem that we're actually trying to tackle in this section. So to explain this, I've prepared a flowchart. So here's what I want us to solve. Okay. So let's say you run an e-commerce website and users can leave feedbacks on the products that they have bought, right? And depending on the type of the feedback by the user, right? It could be a positive feedback by the user. It could be a negative feedback, right? It could be a very, very bad feedback that requires escalation. I mean, depending on the type of the user feedback, the response from the customer support agent would vary. So this customer support response is exactly what we're trying to automate here with LangChain and AI. Okay, so we're just going to analyze basically how the user is feeling looking at the review, whether it is positive or negative or basically just a neutral feedback, or it is a very bad feedback and the user is like really mad and we have to escalate it, right? So we are assessing that, and accordingly the AI is going to respond to that particular thing. So first off, we are taking the user feedback and then we're sending the feedback to the model, asking it to tell whether it is a positive feedback or a negative feedback, a neutral one, or if it requires escalation to a human agent. So right here, we would have categorized the feedback. The next thing that we have to do is, depending on the type of feedback, we need the control flow to go to different branches, right? So the first branch is for the positive feedback flow. The second one is for the negative one. And we have the neutral branch. And finally, we have the escalate branch as well. So essentially, we are conditionally sort of making a decision to go into any one branch. So in the previous section, we talked about parallel branching, where all the branches start firing. Whereas in this section, we have multiple branches or multiple chains. And based on one condition, it is going to go to the first one or the second one or the third one or the 100th one, right? So I hope that makes sense. Let's actually jump back into the code and see how to execute this. So you can see I have all the code ready already. Let's go down, let's scroll down to the chain, and let's again try to work backwards, right? So here is the chain. And first runnable that we're going to call is the classification chain. So if you remember from the diagram that we saw earlier, we are first going to take the user feedback and then decide the type of the feedback. And this is a chain in and of itself, right? It might look very simple, but it's actually a little abstracted. If we go inside of here, we can see that first we are preparing a template. And always remember, anytime we talk to the model, we make a call to the model, we first have to prepare a prompt template, right? Basically saying like, hey, what type of feedback is this review, right? So let's look at the prompt now. So we're just saying you are a helpful assistant, and we're saying classify the sentiment of the feedback as positive, negative, neutral, or escalate, right? And we are providing the feedback here as well. Okay, so if you scroll down, you can see that we are providing the feedback inside the object. All right, now let's come back to the classification chain. Now the model is going to spit back the keyword, right? It could be just a keyword called positive, negative, neutral, or escalate, right? So now we have the condition ready as well. So if we come back to the diagram, we now have the type of the feedback, which is going to be the condition, and that is ready. Now we have to decide which exact branch it should go inside of, right? So let's see how we've done that. So now the type of the feedback is sent inside of this next chain called branches. So let's click on it and let's see what we have done here. So what we have here is like a switch case, right? Where if X, which is going to be the feedback type, is positive, then this chain will execute, right? If it is negative, then this chain. And then we have the neutral and the escalate at the end as a final default case if it cannot find a match above. Now let's say the feedback was positive, right? What do we do then? So what we might have to do is we need to send that feedback message to the LLM and ask it to provide a positive response to the positive review, right? So if I actually click on this, you can see that it says generate a thank you note for this positive feedback. And then we are providing the feedback here as well. And as soon as the response comes from the LLM, what do we do then? Let's scroll down. So we are getting the response back from the LLM, and now we are extracting the content property from the object. See, the branches is at the end of the chain, so it gets printed to the console. That's it. So the same thing applies for other types of feedbacks as well, right? So if it was a negative feedback, the prompting is going to be a little different. So we are going to say, generate a response addressing this negative feedback. Basically, if the user is super frustrated, then the control flow will go inside of the escalate chain, and this is going to be the prompt. So we are saying generate a message to escalate this feedback to a human agent, right? So let's actually try to run this file. So currently you can see that this is the review that I've hard coded here. The product is terrible. It just broke after one use. So clearly this is a pretty negative review. So if I run this in the terminal, let's give it a few seconds. All right. So you can see that it gives a proper response to the negative feedback from the user. It apologizes for its service, and it's asking for more details the user faced. And right here, I've also added more feedback examples for different types, like a happy user, a neutral user, a negative, an escalate as well, right? So you can just like play around with these different reviews and then see where the control goes. And just to remind you, all the code that we've written so far, it is available in the repository. So do go ahead and pull it. And yeah, that's it. That brings us to the end of the chains module. I really hope that you're confident enough to architect or construct your own chains based on the business problems that you're currently facing. And again, if you ever get stuck, do join the community. It could be me or some other developer could come and help you out. In the next section, we are going to be looking at the fourth component of LangChain. And in my opinion, it is what is creating a lot of impact in how businesses operate and increase efficiency as well. And that component is called RAGs, or Retrieval Augmented Generation. And it's kind of I would say, the most difficult to get to wrap your head around, but at the same time, it would make you a really valuable developer. So we'll be diving completely into it in the next section. So I'll see you there. Hello everybody. In this section, we're going to start looking at the fourth component of LangChain called RAGs, or Retrieval Augmented Generation. So in my opinion, I feel that RAGs is a pretty misunderstood topic because it can be a little tricky for beginners to understand, especially if you are completely new to the concepts like embeddings and vector databases. All right. But don't worry, we are going to be taking it slow, step by step. All right. So what is RAGs and what is the problem that it solves, right? So to answer the question, RAGs solve just one problem with LLMs, okay? Just one problem. And that is giving LLMs additional knowledge. Just remember that for now, okay? It gives LLMs additional knowledge. Or in other words, RAGs basically just provide an external source of information to LLMs so that LLMs can better answer the user's questions. So this is the first problem that it solves, right? So if you don't understand it, let's explore a very simple example. So let's say you work at a company with hundreds of internal documents, right? Let's say things like policy guidelines, technical specs, customer support documents, right? So these are private documents that the LLM does not know. Okay, just know that. Now, let's say you have a question that could be answered by any one of these documents, right? What you would normally do without AI, what you would normally do is you'd basically normally comb through each and every single document trying to find your answer, or you would just ask a colleague or something, right? But with AI and with RAGs especially, we can really streamline this entire process, right? So what you're going to do is, instead of going through all the files manually by yourself, right, that which is like the most least efficient way of doing things, right? Instead of doing that, what we do is we make all of these private data available to the LLM. Basically, we give this external source of information to the LLM, right? So the next time you have a question, you can just ask that question in plain English. And now that the LLM has access to all your private information, it is now able to comb through all your data and then give you a very informed, accurate answer, right? So that is the power of RAGs. But this brings us to another important challenge, right? There's a challenge called context limits or context window, right? That is something that you probably would have experienced it, where if you give large, huge prompts to the LLM, it really struggles to answer the question, right? It really struggles to, it sort of starts hallucinating, and it sort of starts to forget what happened before that in the past and all of that, because the context window or the limit becomes very high. So we can't really dump all our private documents into ChatGPT, let's say, and then ask a question on it, because that is not going to work, right? So this is the second problem that RAG solve, which is with context limits. You can make all these PDFs and everything available to the LLM without having to actually dump all of it into a prompt. Let's say you have, 100 or 1,000 documents sitting in your own private database, right? So RAGs, the way that it solves this is by only pulling in the relevant sections of the documents based on the prompt that the user provided. Okay, so this way we keep things efficient. We only extract certain chunks from all the documents that are relevant to the user question and then send it to the LLM. Okay, so that's why it's even called RAGs, or Retrieval Augmented Generation, right? So let's actually look at a much better definition. RAGs is a method where we combine LLMs with a retrieval system. So this retrieval system can search through vast sources of external information like documents, databases, knowledge base, whenever the LLM needs additional knowledge to give you better answers. So all the while making sure that the LLM is not overwhelmed with bigger prompts. So this section was just a very high level introduction to RAGs. I don't expect you to completely understand it, but in the next couple of sections, when we actually start splitting the entire RAG module into all its individual components, it is going to start making a lot of sense. And that is exactly what we're going to be doing in the next section. So I'll see you there. Hello guys, in this section we are going to be breaking down the entire retrieval augmented system and looking at each of the components so that we can see what exactly is going on, right? So I'm going to be using the same example that we saw in the last section. And as you can see up here, we start with a few hundred PDFs or basically just like a lot of text documents that are private, right? So we'll be doing something called chunking right here. Okay, so we'll be learning terminologies like embeddings, vector store, and how the retriever works right here. So once you understand how all of these individual pieces come together to form the entire RAG system, the actual coding aspect itself is actually kind of a cakewalk and it's very simple. All right. So what I'm going to do is I'm going to split this section into two different parts. Okay. So in the first part, we're going to go over this first process right here, which is going to basically take a huge amount of private text, in this case, a lot of documents, and then make it go through several processes and finally save that in a very special type of a database called a vector database. And once we're done with that, in the second part of the section, we're going to be seeing how a user can ask a question. Okay, something like, let's say, what are the company's policies on remote work, right? And then this component called the retriever retrieves only the relevant parts from these documents. Okay, so once the retriever has both the relevant parts from the document plus the user's question as well, it sends both of that information to the LLM so that it can give an accurate, well-informed answer. So this was a very quick glance on the entire RAG's workflow. Let's actually deep dive into the first section of this workflow, where we're going to be converting all of these documents and text into a certain format and store all of that in the vector store, right? All right. So in the flowchart, you can see that there is a PDF that is insanely big, right? So in other words, this is 10 million tokens long. So if you do not know what tokens are, let's first understand that, right? So what is a token? So in the context of language models, a token is a unit of text that the model processes. Okay. So tokens can be as short as one character or as long as one word, depending on the language and the structure of the text. For example, the word hello is one token, while the phrase I am is typically broken down into two tokens, I and M, right? So tokens are crucial because LLMs have a limit on how many tokens they can handle at once, often referred to as the context window. So this means that if we have a PDF that's 10 million tokens long, we cannot feed it to the model in one go. Okay, why? Let's actually look at the context windows of different popular models out there. So GPT 3.5 Turbo, which is the model that you get access to on your free ChatGPT version, right? In this free version, you can only send 16,000 tokens at any given time, right? GPT-4 though is somewhere around 130,000 tokens, right? And Google's Gemini right here is at the highest at 1 million tokens. But in our example though, we have one PDF or several PDFs, it could be anything, worth 10 million tokens, right? So it is impossible to dump all of that and ask a question to the LLM, right? It will complain that it's too long, right? And it's not a scalable solution either, because think about it. Right now, yeah, maybe Google's Gemini has the context window so that you can dump all your private documents and ask a question on top of it. You can do that maybe, but let's say in the future, your document size grows, right? And Google's Gemini's context window might remain the same. So it is not really a scalable solution, right? This is exactly why in the RAG's system, we are going to be putting all that text documents through a process called chunking, which is going to be step 2, right? So let's see what chunking is, okay? Chunking is a process where we can split big documents into several smaller chunks. And you can see here that, each chunk is worth 1,000 tokens, right? So if each chunk is worth 1,000 tokens, then you can do some simple mathematics in your head and we can probably say that we now have 10,000 chunks, right? Because 10,000 chunks into 1,000 tokens each is going to be 1 million. Again, we're just chunking it because we cannot dump all these large files into ChatGPT. But if we make smaller chunks and based on the user prompt, this component, the retriever, which we'll get to in a second, okay? So this retriever, what it will do is, it will go query only those relevant chunks based on the user's prompt and then pass it to the model along with the user prompt, okay? So by doing this, we can pass in not just one or two chunks, but actually a lot of chunks, right? if each chunk is like 1,000 tokens, and the free version of ChatGPT even accepts like 16,000, right? So we can pass in like 12, 13, 14 different chunks, and in addition to the user's prompt, which could be 1 or 2 tokens, right? I mean, not 1 or 2, but 1,000 or 2,000 tokens, right? So yeah, we also have a lot of room for the user's question as well about those chunks. So this way we will have some more room for the user's question as well about those chunks, right? So we now know that we sort of break everything down into several chunks, but what exactly is a chunk? What does it have, right? So if you're wondering, basically they're just plain text, right? So if you imagine this to be a 500-page book, and we also know that each chunk can only have 1,000 tokens, then each chunk can be thought of as just like 4 to 5 lines or a small paragraph like this, right? And the next chunk is going to be the next 4 to 5 lines. So it's a continuation. The ordering is maintained as well, right? All right. So we've chunked it. What next? So far we've just taken a huge text, split it into chunks. Now our next goal is to extract only the chunks that are relevant to the user prompt, collect only those particular chunks, and then send it to the model along with the prompt. So that's what we got to do second, right? So we have to ask ourselves a question: how can we actually query only the chunks that are relevant? Okay, after all, we can't just brute force search and check for exact words that match with the prompt, right? That's kind of like an old school dumb way of doing things, right? We need to be collecting the chunks based on meaning, not the exact word itself. And this is where the concept of embeddings and vector databases come into play. It lets us search for chunks semantically, or in other words, based on meaning, and not look for exact words or letters. So in the next section, we're just going to quickly take a detour, look at what embeddings and vector databases are, and then come back to this particular RAGs. All right, so I'll see you there. Okay, so in this section, we're going to be talking about embeddings as well as vector databases, right? So basically they work together. So let's actually start with embeddings. What are they? So to put it very simply, a vector embedding is a mathematical representation of words, sentences, or even images. So for example, the word cat can have a vector embedding that can look something like this, right? So this is the computer's way of making sense of the word cat. But what exactly are these numbers, right? And just for your information, this is how ChatGPT works under the hood as well, right? So it's going to be pretty interesting. So basically, each of these numbers can represent a certain aspect of the word cat. So the first number here in the array could represent the size of the cat. Okay, so if there was a similar representation of the word, let's say kitten, then the first value of the kitten vector embedding would be closer to 34, right? Because they are, with regards to size, they are much similar, right? Compare that to, let's say, an elephant. The embedding for the elephant, the first number can be much more farther away from 34 because the sizes are very different, right? Now, we can think of the same thing for the second number as well. So let's say the second number might represent whether it is a pet or not, right? So if we vectorize the word dog, then the second value in the vector would be closer to this because both cats as well as dogs are pets. So it's going to be closer. Now, picture this, all right? Picture this. Each of the values are actual coordinates in a multi-dimensional space. Okay, so let's take a very simple example in the form of a 2D graph. We know that the words cat and kitten are almost similar in meaning, and their vector coordinates are also very similar, right? So this is why we see the words cat and kitten closer together in the map and is farther away from something like mango, because all the coordinates are going to be different because in almost every single aspect they are different from each other, right? But this is just a very simple 2D map example, all right? But in reality though, the vector has hundreds of dimensions that has some information about the relationship between words and sentences and etc, etc. So basically words and sentences with similar meaning hang out together like right here, and then something unrelated will be farther away from it. So once we create a vector embedding, we can then store it in a database. A database built to store all of the vector embeddings is considered a vector database, right? So what do databases do, right? It basically lets us retrieve information or update information or do something like that, right? So as you can imagine, this vector database as well, it enables us to retrieve information based on meaning rather than exact word matches, right? So I hope that you're starting to understand what vector databases are and embeddings are. So let's actually now jump back to what we were doing in the previous section, which is RAGs, right? So let us see how all these concepts sort of play out there. So I'll see you there. So now that we know what embeddings are and what vector databases are, let's actually continue with the flow. So we have split the big document or a huge book or pretty much anything into several chunks right here, which is going to be the first step. The second step, we are converting each of those chunks into vector embeddings. Remember, vector embeddings are mathematical representation of texts in the chunks, right? So how can we convert it? We can use the LLM embedders, and again, there's a lot out there, but OpenAI provides us with an embedder API that lets you convert simple text into embeddings. And that's exactly what we're going to be using in this course as well. So once we've converted it, we're then going to have all the embeddings for each of the chunks. And finally, we are going to store all of that in the vector store. All right. So note that we store the actual plain text plus the embedded version of each of the chunk. Okay. So each of the chunk in the vector store is going to have the embedded version as well as the plain text version as well, right? So now our entire book or PDF or just pretty much any private data is completely present in our vector store, right? So because of this, we can now query only the relevant chunks based on the user question and then get back the actual text, right? So this brings us to the second part of the workflow. So we'll explore that in the next section. Now let's look at the second part of the workflow. It starts with the user asking a question about the book. Let's say the book is Lord of the Rings, right? So let's say the question is, what is the name of Frodo's sword, right? So now what we do is we also convert this question, that prompt, into an embedding as well. Okay. Now the next thing is we have a retriever component right here that takes this embedding, which we know is the mathematical representation of the prompt, and then asks the vector store, hey, give me the top 5 relevant chunks for this particular question. Okay. And the vector stores basically have very low latency, meaning they're very fast because they're working with numbers, right? So this vector store with its extremely low latency and high speed gives back the top 5 chunks with the highest relevant scores. All right. So at this point, we have two things. We have the user's question right here in English, as well as the passages from the book in the form of smaller chunks that answers the user's question, chunks that are relevant to the user's question. All right. So now we have the top 5 chunks, right? Now what we're going to be doing is we're going to send both the question in plain text as well as the chunk in plain text to the LLM, right? So now the LLM has all the relevant passages and also the user's question. So the LLM is now able to sort of reason and give a very informed answer. And finally, the LLM is going to respond back to the user right here. I hope you now have a full picture of RAGs and how they work. Now, RAGs are pretty great when it comes to, giving our private data to the LLM, basically giving it this additional data, and we can sort of chat with our data, right? So that is one use case. We can also, there is another way of looking at RAGs. Okay, we can also think of RAGs as giving long-term memory to LLMs, right? So I'll give you a very simple example. So I'll give you one final example to better understand this. Let's say there is a customer support bot. Okay, so all the past conversations with a specific user can be stored in a vector database so that in the future, if there is a specific question from history, RAGs can go and retrieve that particular relevant chunk and give more accurate answers. So in the next few sections, we are going to be looking at how to code all of this with the same example that we saw right now. And you'll see it is actually much more simpler than it looks. So I'll see you in the next section. Welcome to the first code example inside the RAG module. So in this section, we are going to be implementing the same exact thing that we saw in the diagram earlier, which is we are going to have a document. In this case, it's going to be the Lord of the Rings book. Technically, it is a book, but we can think of it as a large collection of texts. All right. So I've split the code into 2 parts here so that we can understand it better. So in the first part, we're going to be implementing the first part of the diagram. So if we come back here, first, we're going to be loading the document or the book or the collection of books, load it, and then we are going to start chunking it. Next, we are going to convert each of those text chunks into vector embeddings. And finally, we are going to be saving all of those embeddings along with the original texts inside to the vector store. Okay, so for our code, we are going to be using the ChromaDB vector store. And it basically lets us save our embeddings locally as well. So we don't have to use cloud for that. For this section, we have to install 2 additional packages. So you will have to run the command pip install ChromaDB, and this is going to have all the core modules needed to create the vector store. And we also need LangChain-chroma package as well. This is going to be the wrapper that connects our LangChain application with the vector store. So now that we've installed all the necessary packages, let's dive into the code. So we know that the first thing that we have to do is to load the document, right? So to load the document, we need to know the path to that particular document, right? And that is exactly what we're doing here. So this dir_name method is going to give us the path to the current directory the file is in, and we are inside this 4_rags directory, right? So now that we have the current directory, we can then go inside of the documents and then the name of the book, and this gives us the file path to the book right here. Okay, so this is just very standard Python stuff. All right, so now this is where the actual vector stores come into play. Now we need to provide a directory in our project for the ChromaDB to go ahead and create its vector store. Remember, we are going to be storing all of our vector embeddings locally and not in the cloud, because we're just learning, right? So I'm just going to tell it to create a folder inside of our current directory, call the folder db, and then create a db file inside of it called chroma_db. Okay, so we've named it persistent directory because whatever is going to be saved there is going to be persisted. As in, it's not going to be erased every time we stop the application and restart it. Okay, so if we go back to our diagram right here, in this step, we have all of the chunks, converting it into embeddings, and then we are going to be storing all of that content in the database, and this data will persist so that we can use it at a later date. All right, next, I've got a very simple check here saying that if this DB file is already created, we don't want to be running the same thing again. Why? If we come back to the diagram, the text to embedding process, it costs a little bit of money, right? Because we'll be using an API to convert it, right? So we're just making a check right here saying that only if it is not created already, we allow it to go inside of here. All right. So let's see what happens inside of this. So it says persistent directory does not exist, initializing vector store, right? So we're starting the process, but in order for the process to start, we actually need this file in the location. If we don't have this file inside the documents folder, we're just going to throw an error saying that the file does not exist. Let's keep going. Now we know the exact path to the book as well as the path to the DB. Next up, let's load the book. So this is going to be the first step, right? So we are going to be using the text loader class that I'm importing from the documents loader module. So this will help us basically load the document in memory right here, like basically assigning a value to a variable. So once we've loaded the document, or it could be multiple documents, right? We are going to start chunking it, right, into smaller texts. So to do that, we are going to be using the character text splitter class that if I scroll up here, we've imported it from the text splitter module. So this takes care of chunking how much ever documents you provided. Okay, so we are initializing it saying that we want each chunk to have 1000 characters, and we currently have the chunk overlap set to 0 as well. So what is this chunk overlap, right? So let's look at that. Chunk overlap defines how many characters or tokens, depending on the splitter, should be included in both the end of one chunk and the beginning of the next chunk. So by setting the chunk overlap to 0, you are telling the splitter to ensure that there is no overlap between chunks. If we set the chunk overlap to 100, for example, the last 100 characters of one chunk will appear at the beginning of the next chunk. So this helps preserve context across the chunks. All right. This is an example of two different chunks. You can see that the first chunk ends with the sun was set, and the second chunk begins with ting and the shadows of the tree, right? So this is the reason why we have to add a little bit of overlap. Okay, so we ideally want to maintain as much information within a particular chunk. So that is why we add some overlapping, right? So by adding this extra overlap, we ensure that the model doesn't miss important context while processing chunks independently. Okay, so secondly, it also helps with semantic understanding, especially when we are working with large texts. It could be like books, right? Chunking with overlap can help with better understanding across the chunks when querying or processing. So let's get back to the code and let's add some chunk overlap here as well. If you're working with complex texts like essays, novels, etc., it's better to give it somewhere between 20 to 100 characters. So I'm going to give something like 50. If we're working with a simple text, 0 is also fine, but I'm going to leave it at 50. Let's move along. So now that we've chunked it and now we have an array of chunks, it could be 20, 50, 100, right? So we'll print that as well to look at the length. So the next step, if we look at the diagram, is to convert each chunk into its vector embeddings version. So we're going to be using the help of this particular model right here, the text embedding 3 small. Okay, this is by far the most capable embedding model by OpenAI. That is also, I believe, very cheap as well. There is also another model called text embedding 3 large. Okay, so if you want your vector embeddings to have a lot more numbers in the array, then you can go for this large model. Okay, so of course, for this tutorial, we're going to be sticking with the small. Okay, so this, I believe, does the job pretty well. Once we have all of the embeddings right here, the next step is to store them in the database, the vector database, right? So if we come back to the diagram, we store the embeddings as well as the corresponding texts in the database. And that is exactly what we're doing here, right? So we pass in the docs as well as the embeddings to the store, and exactly where to store it, that is in this particular directory, right? So let us go ahead and run this file. So I'm going to click on the play button. Also note that there isn't any folders, database folder, database files that are not created just yet, right? So if I run it, let's give it a few seconds. And great. So now you can see that the embedding process has been done and it's been successfully stored in this file right here. The same chroma DB that we specified above in the code. So if I scroll up right here, we can see that we have several logs, right? What were the processes it went through, right? It says created a chunk, right? And the total number of chunks is going to be 40 something. Okay, and we've also printed the first chunk to the console, the very first chunk, and it's nothing but the first few, like the first 10 lines of the book, something like that. So it says the book is largely concerned with hobbits. And if I go into our book right here, you can see that that is exactly what we have at the very top, right? So the first step in the whole process is done. We have stored our private data in the vector store. Now let's actually go to the part 2 of the code where we're going to be looking at this particular part of the system. All right, I'll see you there. So in this part of the section, we are going to be looking at the second part of the RAG system where we're only going to be pulling the relevant chunks from the database, the vector database, based on the user's prompt. So let's go through it step by step. So we already know that the book is vector embedded and is now present in this file right here, right? So to start off, all that we're going to do is referencing our current file to the DB file. Okay, so we're taking the current directory, and with that, we're piecing together the exact location of the chroma DB file. Okay, and then we're loading the vector store, in this case, the chroma DB right here, so that the database is available to use inside of this file. So, right, first we need the database to be available to work with, right? So that is what we're doing right here. We're telling it this persistent directory is where the database exists, and later if you want to embed the user's question as well to search the database for the right chunks, we can use this embedder. And again, we're specifying the embedding model that we're going to be using. Now, this is something that a lot of people seem to get wrong, right? So whichever embedding model that we used to embed your private data, we have to use the same model to embed the user's question as well. Okay, you can't use different models or else it's not going to work, all right? So in this case, we're constantly always sticking to the text embedding 3 small model. Okay, just remember that. Now, the next step is to set up our retriever, and then we are going to configure the retriever. All right. So if you remember from the diagram, the retriever is basically what collects the relevant chunks from the database based on the user's prompt, right? So we can configure it by mentioning the type of the searching that we want to do. So in this case, I'm using the similarity score threshold searching type. But in the next few sections, we're going to be doing we're going to be exploring different types of searching, right? So, and then we're going to be using the search KW args. Okay, so what does this mean? We're specifying just how many highest relevant chunks that we want the retriever to bring. Okay, so in this case, it is going to collect the top 3 chunks with the highest relevance scores. And right now, we're saying the similarity score needs to be at least 0.5 or higher. Okay, so this is a scale that goes from 0 to 1. So it is going to collect all of the chunks that have the similarity scores that is higher than 0.5, and it is going to shortlist the top 3 and then give it back to us. All right. So now we've set up our retriever, we've configured it. The next step is we have to query the relevant chunks based on the user's question, right? So once again, I'm going to be using the magic keyword invoke right here. If you remember, this is the magic keyword that we're going to be using to take action in LangChain. So once we run this, it's going to give us the top 3 relevant chunks. So let's actually go ahead and run this file. We're also going to be playing around with these parameters, see what happens. So remember, all that we're doing is printing the relevant chunks right now. Okay. So if we run it, let's wait for a while. And great, we have a response. I right now expect 3 different docs, or basically 3 different chunks that relate to the user's question, right? So we know that the question is, where does Gandalf meet Frodo, right? So let's actually go look at the first chunk, see if it actually contains the information required to answer that question. So you can see it says, it was in the heart of Hobbiton, at the home of Frodo Baggins, that Gandalf came to speak of matters far greater than Frodo could have imagined. And this perfectly answers the question, right? How amazing is that? So Gandalf meets Frodo at the heart of Hobbiton in Frodo's home, right? So let's look at the second chunk. Here it says, Gandalf came to Hobbiton to visit Frodo one summer day. This answers the question as well, right? And finally, let us look at the last chunk. Frodo was in his home in Hobbiton when Gandalf arrived, his old friend and mentor. That's amazing, right? The exact passages that contains the answer have been retrieved. So now you can actually pull this code, change the parameters right here, and then see what happens as well. So now we can say we need the top 10 chunks, let's say, instead of 3, and we are lowering the upper limit as well. So it's going to bring in a lot more results, as you can imagine, right? In the other hand, if we become a little too stringent, so let's say I'm only saying only collect the chunks that have a similarity score of 0.9, right? So let's see what happens, and then run it again. Okay, so you can see that it says it cannot find any relevant docs because using this particular threshold of 0.9, right? So if you're building your own RAG applications, you might be, mistakenly be a little bit more stringent with your score. And this is the lesson. You can't really go too high or low. You have to find the right balance, right? And that brings us to the end of this section, where we basically just dealt with one full book and then we implemented a RAG search. In the next section, we'll actually see how we can add metadata to each of the chunk. So what I mean by metadata is basically being able to add, more information about where the chunk came from. For example, this particular chunk came from this book, this chapter, this passage, etc. So that in the future, by retrieving it, we'll actually be able to see where the source of the chunk came from. We'll also see why that is helpful in real world applications as well. So I'll see you there. In the second example of RAGs, let us see how we can introduce metadata into our chunks. So first, let's talk about why we even need metadata. Let's say we put 100 different private docs or books into our vector store and we ask a question. In addition to getting the chunks, it will be better if we also know where the chunks originated from, right? For example, like it's this particular book, chapter 4, paragraph 3, or this particular document, this section, paragraph 7. So it gives us extra information on where the chunks came from. So if you think about it, it is very similar to what ChatGPT search does as well. When we ask a question, it crawls the web, gives you a response, but at the same time, it attaches a source URL as well. Like these are the websites I took the answers from. So this way, we know that the answers are legitimate and it is not just hallucination. Another example could be, we could store transcripts from a meeting in the vector store, and 2 years from now, we can chat with a model, ask it what was discussed that particular day, and it will give me the answer along with the source as well. So we can just click on that particular link and go further explore manually. So sky is the limit. So to help with this particular example, I've added a lot more books and prepared code for this section as well as the next few sections for RAGs. So let's jump into the code now, and you will find that it's not really that different to what we've written earlier in the previous section. First thing, we need to pull all of our new books into the vector store so that we can start asking questions, right? So I've added a few more books right here, like Frankenstein, Dracula, etc. And these are pretty long books. Now let us chunk all of these books, embed them, and then put them in the vector store. So first thing, we're getting a reference to the documents directly. And then we're also telling LangChain to create our vector database containing all of these books in this new file called ChromaDB with MetaData inside of the DB folder. So we're using a different database file this time. I've already run this file, so I already have the full embedded version of all of my books in this database file. And the rest of the code is very identical to the first example we saw. We're checking if the database is already created or not. If it's already created, we do not go inside of this if block. So coming in, this is where it's slightly different. Basically what we did the last time, but this time we're embedding several books. So the first thing that I'm going to do is go inside of the documents folder and search for all the files that have a txt extension. As you can see, I've got all the books with the txt extension. And this line is going to grab all of those book file names and put it in this array. All right, now we're looping through all the book file names, and with each book file name, I'm going to load it in memory using the loader, and I'm going to add it to the final documents array. Very similar to what we did earlier, but instead of just one book or document, we are doing several right here. But there is one more additional thing that we're doing. Along with the document, we're also going to be adding a metadata to each document. Okay, so we can have as much information that we want, but for now, I'm just saying source and I'm adding a book file to the source. So if I'm loading the Frankenstein book, the book file name is going to be Frankenstein. And from here on, we're going to go through the same process. We're chunking the entire list of books, and then we're specifying the embedding model that we're going to be using to embed, which is going to be the next step. And finally, we are creating the vector store by providing the docs, the embedding model, plus the final DB file it should create and put all of the embedded data in. And as I already told you at the start, I've already ran this file, so I already got the DB file created with all the chunks embedded. So let's now go to the next section where we can actually ask questions to the RAG system. So what we're going to do here is pretty much the same. We point the file to the new DB location that we've just created a minute ago. So this was the DB name, if you remember. So this line loads the DB file up. So we provide the location as well as the embedding model. So here is the query that we are going to be asking. So it is going to be, where is Dracula's castle located? If you're familiar with Dracula, he's a vampire that lives in a castle. And this is the question that we're asking. And obviously, somewhere in the book, the location of the castle will be mentioned. So our super intelligent RAG system is going to retrieve the relevant chunks when I run this file. So let's look at the next piece of code. And here we're configuring the retriever. We're still going to be using this type of searching, the similarity score threshold. And we're also going to be specifying the count should be 3 and the threshold value should be 0.3. This is the number that works for me because if I reduce this, it doesn't give me any results. So in your applications, you will have to find the right balance. And finally, we are going to be using the magic keyword invoke. And if you remember, it does two things, right? It converts the user question into an embedding. And now, And now that we have a query that is in an embedding vectorized format, the book content, which is also in a vectorized embedding format, it goes out, queries the top 3 chunks. And finally, it prints out all of the chunks. So I'm pretty excited to run this file. Let us see if we're able to find the answer in the retrieved chunks. But let's run this file. So it's going to take anywhere from 4 to 10 seconds. And amazing. We now have 3 chunks, and these are pretty big chunks. We know that Dracula exists in this town called Transylvania. If you've watched any of the animated movies, etc., etc. So let us actually see if the term Transylvania is present in any of these retrieved chunks. So as you can see, we have Transylvania mentioned in the 3rd line and also in the 7th line. I had visited the British Museum and made search among the books and maps in the library regarding Transylvania. And also down here, it is giving the exact locality of the Castle Dracula. So with just this one paragraph, even a human can deduce that Dracula lives in Transylvania. And even more importantly, we can also see the source of the chunk, which says dracula.txt. Because if you remember, we added the book names as metadata to each of the chunks. So let's now move on to the next chunk and let's search for the term Transylvania. And you can see that it is not listed in the 2nd and 3rd chunks, but it probably gives more information that the Dracula does live in Transylvania. So you can see that it says, thus, when we find the habitation of this man that was, meaning the Dracula, so it is still talking about the location of the Dracula. So we only have 3 books right now, but imagine 100 books, 1000 books or private company documents, right? And how RAGs basically allow the possibility of chatting with it in natural language and be able to get that answer, right? So I hope that you're starting to see the power of RAG systems. So that is basically how we can add metadata for each of our chunks, all right? So the next step is basically to send all these retrieved chunks along with the user's question to the LLM so that the LLM can actually look at the chunks that might potentially have the answer to that particular question, and it is going to give us the answer, which is going to be, in this case, Transylvania. So we will see how we can do that in the next section. So what I've done is I've copy pasted everything from the previous section in this new file, but in addition to it, I've also added a little bit more code as well. Okay, so let's look at what we're doing step by step. So far, we have the user prompt as well as the relevant chunks that are getting generated based on this question. So the first thing that I'm going to do is very simple. First, I'm preparing a combined prompt to the LLM saying, here are some documents that might help answer this question. So here we can put the actual user question, which in this case is, where is Dracula's castle located? So we provide the prompt. Now we need to provide all of the relevant chunk texts. If you remember, we shortlist the top 3 chunks and we're providing that here as well by joining these docs together. Very simple. And to make sure it works, this is what I'm going to do. I'm going to say, please provide a rough answer based only on the provided documents. If the answer is not found in the documents, respond with, I'm not sure. So we're doing this so that the LLM only answers the question from the chunk texts provided. Now we're instantiating the model. So we've done this several times now. We're defining the messages array with the system message as a simple, you are a helpful assistant. And finally, we're going to invoke it and print the result. Let's actually comment this out so that we're only interested in the content. So let's actually run this file and give it a few seconds. And we have the final result, and let's see what it says. Based on the provided documents, Dracula's castle is located in the extreme east of Transylvania, just on the borders of Transylvania, Moldavia, and Bukovina, in the midst of the Carpathian Mountains. The post town named by Count Dracula is Bistritz, right? I can't pronounce it either. How amazing is that, right? The LLM is able to identify this based on all this data that was present in the chunks. So let me show you. Let's copy this word Bistritz and search for this, and you can see it shows up in multiple places in the chunks, right? Just how amazing is that? Let me ask another question as well. So let's say, okay, so we all know that the Dracula hates garlic, right? So let's ask that question. what does Dracula fear the most? So now let's clear the terminal and now let's run this file. Okay, so we have the response. Let us see what it says. It says that Dracula fears a lot of things. He cannot enter places unless invited. Does not like garlic. Wow, right? It gives the answer and it's given a lot of other things that we even did not know. Let's actually confirm if the LLM gave this answer based on the chunks we sent it. So I'm going to copy this word garlic and search for it. Scroll up and you can see this is mentioned several times in the chunks. How amazing is that, right? See, it says he is afflicted by garlic. He also does not like crucifixes. So if I scroll down all the way, you can see that the LLM also assures us that it only took all of this based on the provided documents. So this way, we know it didn't go into its own knowledge or do an internet search. So in your own projects, instead of doing it with books, you can put in your private data that the LLM has no way of knowing and give it additional knowledge and chat with it. And we can even take it one step further. So instead of it being a one-off question, you can build it in such a way that we can have a to and fro conversation as well. Okay, so if you remember, we already did that in the chat models module, and you can implement the same thing here. And with that said, we've completed our deep dive into RAGs. Take a moment to appreciate, how far we've come. You are currently in the top 5% of developers who can build RAG systems and build these intelligent retrieval systems using LangChain, right? So you can now build intelligent document retrieval systems, create context-aware conversational AI, connect AI to your private data, and even integrate web crawling abilities, right? So if you're finding value in this journey, please don't forget to click the subscribe button, because it really helps the channel grow. But at the same time, it gives me more incentive to make more advanced AI related content, right? But yeah, guys, we're not done yet. Up next, we're going to dive into the fifth and the final component of LangChain called agents and tools. Okay, so this is where it gets really interesting. Imagine basically giving your AI the ability to actually use tools and make decisions like an actual human being, right? So if that excites you, we're going to be exploring that in the next section. So I'll see you there. Welcome to the last and final component of LangChain called agents and tools. You know that moment when you hear AI agents and you think that it's going to be super complicated. I felt the same way when I started it, but here's the thing. It is actually much more simpler than it sounds. Okay. And by the end of the section, you'll be wondering why were you even worrying so much. You can think of agents as the problem solvers of the AI world. Agents are capable of thinking on their own. So in other words, it's AI that can make autonomous decisions. We learnt about chains and RAGs, right? They follow our specific instruction, but agents, they actually take it a step further. They can decide for themselves what steps to take on their own. If that sounds too complex to understand, don't worry, we're going to be starting from the basics. We will break down what agents really are, why they're such a game changer, and how they solve real world problems. So no complex words, no confusing concepts, just straightforward explanations that will make you say, oh, that's what it means. Okay, great. Let's get started with the fundamental question. What exactly are agents? Think of agents as AI decision makers that can pick the right tool for the job without being told what to use. Just like a chef who knows when to use a knife, whisk, or the oven to create a perfect dish, an AI agent can decide when to browse the internet, or when to use a calculator, or when to make an API call to the database. So right here, we notice this keyword tools, right? So what are these tools? Tools are specific functions that AI can use to complete tasks. Just like a chef's kitchen tools, like knife for cutting, oven for baking, blender for mixing, tools are the special abilities we give to AI agents. Okay, so just like giving a calculator tool or a search engine tool or a calendar tool, right? Tools like Perplexity and a lot of other applications are built using tools only. All right. So now you somewhat must have an idea why we might want to use agents, right? So basically, agents help language models decide what actions to take when solving a problem. They choose the right tools at the right time without us telling them which tool to use. So let's look at a very simple example of using tools. If I ask an AI agent, what is the weather in Paris plus 5? It gets really interesting. The AI agent isn't just randomly picking tools. It is actually thinking through the process, kind of like a detective solving a case. Firstly, the agent saw two parts to the problem, finding weather and doing math. It knows to get the weather first because you can't add 5 to something that you don't know yet. Then it uses the calculator tool to add 5. But you might ask, how does the agent know what to do first and what to do second? This is where the concept of React comes in. This is one of the best patterns in AI today to build agents. And by React, I don't mean the front-end framework. We're talking in terms of AI terms. It stands for reasoning plus acting. So this is basically a concept that mimics how human beings think. So if we look at a problem, what do we do first? We first think about the problem, right? And that's exactly what agents do as well. Think, right? So the second step is act. And the agent can act or perform the task using various tools available. And then the third step is observe what happened. And lastly, repeat the entire process if needed. So let's actually see how our Paris weather equation looks like with React. So first it's going to think. So the thought comes first. I need to find the Paris temperature first. So the action is going to be uses weather, right? It uses the weather API. And secondly, the action is going to be uses weather API. And the third step is the API observation. It's 20 degrees Celsius in Paris. And then again the thought happens, right? It is coming back. It's cycling. So the thought happens. It now says, now I can add 5 to this. And then the action again happens, uses calculator. And then the final answer is going to be 25 degrees Celsius. Think of it like solving a puzzle. Instead of just showing the finished picture, React lets us see each piece being put into place. This is a very small example. Imagine I ask you a much more complicated question like, should I pack an umbrella for my trip to London next week? And what restaurants should I book? You can imagine that this is a multi-step problem, right? And our AI agent might loop through the thought, action, observation, repeat, thought, action, observation, this thing multiple times to solve this problem. I hope you're starting to somewhat get a picture of what agents and tools are. If you don't understand it completely yet, don't worry. In the next section, we are going to be building custom agents from scratch, and we are going to be looking at a lot of examples as well. So I'll see you there. Hello guys, welcome to the section where we are going to be building an AI agent from scratch using code. So by the end of the section, you should have a pretty good idea of how to build agents for pretty much any business use case. And since this is a new concept, we're going to be taking it very slow, step by step. So here's what we'll do. Firstly, I will show you a limitation that we currently have with LLMs, and then we'll see how we can solve that limitation with an agent. So now I'm going to copy paste some code right here. So all that we've done here is loading the environment variables, initializing the LLM using the GPT-4o model again. And I have this question I want to ask to the LLM. What is the current time? Now this query, we're providing this as an input to the chain so that this gets converted into a prompt and gets sent to the LLM. Very basic stuff. So let's run this file again and let us see what GPT-4o has to say about the current time. So let us hit run. Give it a few seconds. All right. So it's saying that it cannot access real-time information, right? And the reason why this happens is because LLMs by itself cannot access real-time data. They are trained on some data and they usually have a cutoff date as well. But if I ask it something that happened today morning, chances are it does not know. And this is a perfect example where we can give more ability to the LLM by creating an agent. And now that agent can then use a tool to figure out the current time. If this sounds too sci-fi, don't worry, we will all make sense of it pretty soon. So now, first off, we need to install a few packages, and the first package I need to install is called LangChain Hub. So let me go ahead and clear my terminal, and I'm going to say pip install LangChain hub. While it's installing, we will deep dive into what this package is, but on a very high level, it lets us use other people's prompt templates from the internet. So instead of writing my own, I'm going to use someone else's. Very simple. So in this example, I'm going to need the React prompt template. Don't worry, we are going to be seeing exactly what the React prompt looks like later on. But for now, let's just go ahead and use it. And let's see what we get. So to do that, what we're going to do is, I'm going to replace this part right here for the prompt template. And instead, we are going to be using the React prompt template from LangChain hub. So I'm going to say hub dot pull, and I'm going to specify the exact repository and file. So it is going to be hwchase17 / react, because we want the React prompt. If you're confused what this is just the organization space of Harrison Chase, who was the creator of LangChain. So inside of this repository, we want the access to the React prompt template. So right now, we are getting a squiggly right here because we haven't imported the package. So I'm going to go up here, say from LangChain, import hub. And now the squiggly line goes away. Perfect. We will look at what this prompt actually contains later on. But for now, let's move ahead and create some tools that we can make the agent use. So I'm going to say tools, and this is going to be a list. We can provide a lot of tools to the agent, and depending on what the agent is solving at that particular point of time, it can use the right tool to get the job done. It could be a Google search tool, an email sending tool, etc., etc. In this case, we need to create the get system time tool, and this is going to let the agent access the current time. We'll get to that in a minute. Now the next thing that we have to do is create an agent. So to do that, I'm going to import something from up here. So I'm going to say from langchain.agents import create React agent. And in addition to this, we also need something called the agent executor. I'll explain to you what all of these mean in a minute. And the later part of the section, we will see how we can implement all of this without all these helper methods, so that you actually understand how an agent is created under the hood. But for now, I'm going to come down here and say agent equals create a React agent. Inside of this, I'm going to pass in the LLM, which in this case is the GPT-4o. I'm going to pass in my tools, and then I'm going to pass in my prompt template, which we are going to be pulling from LangChain hub. And what I'm going to do is, I'm going to remove this chain, and now we're going to declare an agent executor. And then we can assign it to the agent executor class. And this takes in a few parameters. We can pass in the agent equals agent. And then we can also pass in the tools. So tools equals tools. And finally, I'm also setting verbose to true. So we set verbose to true because we want to be able to see what the agent is thinking and what it is doing at every step of the way. It is making it easier to debug and tweak the agent. And finally, I'm going to remove all of this and just invoke on this agent executor. And the input is going to be the query. Everything looks good, and we don't want to print anything because the verbose is made to true. So you're anyway going to see the logs. All right. So to do a very quick recap, we have the query, the prompt which we're pulling from the LangChain hub, no tools we've written just yet, and finally pass in all of this information into the executor, which is going to execute everything. And finally, we are going to invoke the agent with the query. So if I run this, what's going to happen? It is obviously going to fail, right? Because the LLM does not have a tool here to figure out the time. So let's actually run it and see what happens. And great, you can actually see all of the logs as the agent is going through each and every single step, right? So we know that the React agent prompt follows reason, act, observe, repeat, right? And that is exactly what is happening right here. So the first one is reason, and that's what it does. It reasons to itself, I need to check the current time in my current location. So once it reasons what the problem is or what it needs to do, it then needs to do something with it. So that's why the second step is action. It says use a tool to figure out the current time. But unfortunately, we have not provided the agent with a time tool yet. And that is why it says that it does not have any tools to figure out the problem. Or, even if there isn't any tool, sometimes it starts to hallucinate as well. And finally, it gives an answer that it cannot find the current time because it does not know how to solve the problem by itself. So let's fix that. Let's now equip our agent by providing it a tool. So I'm going to go ahead and create a very simple Python function that is going to return the current time. So I'm going to say def get system time, and I want the agent to give me the answer in a certain time format as well. So I'm going to put in the default time format right here. Very simple. I just want the year, month, day, hours, minutes, and seconds. So now that we're done with that, let's now write the function. And to do that, I'm going to make use of the standard datetime Python library that gives you access to the system time. So I can come up here and just say import datetime, and then come back and I can say current time is equal to datetime dot now. And this will give us the current system datetime. And I also want to format the time so that I can say formatted time and then say current time dot strf time and pass in the format right here. So if the LLM decides to not pass in a certain format, then in that case, it will just default to the default format. And that is it. And let's actually return this file right now. And that is it for the function definition. So we have a pretty decent function that returns the current time, but unfortunately, LangChain doesn't actually know what to do with this particular function. So there is one more additional thing that we have to do. We have to add a Python decorator for this function so that we can say add tool. And we can import this by going up here and saying from LangChain dot agents and import tool. So what this decorator will do is basically change this method into a format that LangChain can easily understand, and also provide in this a docstring or a description about the method so that the LLM will have more context about this method. So we can then use this triple quotes and inside of it say returns the current date and time in the specified format. So because of this, the LLM would know if it should use this tool or not for a particular task. So make sure you always give your tool functions a really good description or a docstring. So now all that is left is to provide this tool as an item in the tools list, like this. Perfect. Before we run this file, I want to show you how the control flows so that we get a much clearer picture of how it all comes together. So the first step is what we did was prompt and initialization. You provide a prompt to the agent, such as the React prompt. The prompt includes an instruction to the LLM about its task. Example, reasoning step by step and deciding when to use tools. Secondly, a description of available tools, including their names and usage details. And step 2 is agent execution. When the user provides a query to the agent, the LLM interprets the query and generates a response. The LLM does not directly execute the tools. Instead, it suggests which tools to call and optionally provides arguments based on its reasoning. Step 3, tool invocation. The agent's framework, LangChain, intercepts the LLM's output to check if it suggests a tool invocation. If a tool is suggested, LangChain calls the tool in your Python code, passing in any arguments the LLM has proposed. Step 4, tool execution. The tool runs in your Python environment with access to your Python's resources. like the current time, file system, APIs, etc. The tool returns its result to LangChain. And then LLM responds. LangChain sends the tool's output back to the LLM for further reasoning or generating a final response for the user. So enough theory. I hope you're excited to see how it is all going to work together now. So let's clear up our terminal and then let's hit run. And now it has access to the tool. So as you can see right here, it says it needs to access the get system time tool. So it's reasoning first. And once it is done reasoning, the second step is action. LangChain is now calling our function with the input that the LLM provided as well. In this case, it just took the default format. Then it generates the final answer. And now another LLM call happens with this final data. And the LLM is like, okay, I now have the final answer. And now it displays the final answer. So essentially, what it has done is look through all of the tools and finds the tool that will help it achieve its task and uses it. And it was able to identify the tool with the description that we have provided. Now, we don't have to be super stringent about our prompt. We can actually be a little bit different and maybe even just ask it to tell us the current day or the current year or the current hour of the day. So let's actually try it. So I'm going to add to this, just show the current time and not the date. Now what this is going to do is the LLM is going to send back to LangChain a slightly different input format to this tool. So let's run this file again. Let's clear the terminal and run it. Let's give it a few seconds. And great. Now you can see that the format that it provided to the tool is slightly different. And this time we can only see the time and not the date in the final answer. How cool is that, right? In the reasoning, it is able to see that it just needs to adjust the format to give the right answer. So instead of using the default format, the LLM is suggesting a different format and LangChain executes the tool for us. So once LangChain runs the tool, it takes the result and sends it back to the LLM with all the past context. And the LLM is like, okay, we now have the final answer, and it ends the reason, action, observation loop right here. In our example, the cycle only ran once because it is a one-step problem. Find the current time, so it uses the tool, and that is it. But there could be a much more complicated query, and in that case, the cycle basically could run 3 times, 4 times, 5 times, depending on the complexity of the user prompt. So that is how React agents work. Very, very cool stuff. Let's change the prompt a little bit more this time. This time, we will get it to tell us the time, and I'm right now in India. So what is the current time in London? Okay, and it doesn't know where the system is right now. So we can say you are in India because I'm in India, right? So let's run this. And now if I run this one more time, it should hopefully be able to do the calculation and manually figure out from its own knowledge base, figuring out the time difference between India and London. So you can see it first reasons that it needs to check the system time in India and then convert it to London time. And then it also knows that London is 5 something hours behind India. And it thinks about that too. And now it acts and calls the getSystemTime function, and it now has India's current time. It passes in the right format as well as the tool based on the query. So once it has the right Indian time, it then thinks and reasons to itself, okay, so now we have the Indian time. Now we need to calculate the London time by subtracting 5 something hours. So you can see that is exactly what it says here. So the next step after reasoning action, it says subtract 5 hours from the time. And then it gives the final answer, which is the current London time. And to do the mathematical operations, we can provide our own calculated tool. But most of the times the LLM should be able to do it by itself, but it is always safer in production to provide it our own tools. Because sometimes it will just say, I cannot find the math tool to do the subtraction. So it's always better to be on the safer side. And that is a great demonstration why tools are important. Without the get system tool, the LLM has no way of knowing what my current time is. So far, we've seen the logs of the agent going through the cycle of reasoning, acting, observing, and then repeating the cycle. But how exactly is the LLM able to do it? We know that it's the React prompt. So let's actually look at what this React prompt actually contains so that it's able to do this repeated cycle until it gets the answer. So to look at that prompt, I'm going to go to smith.langchain.com/hub/hwchase17. It might ask you to log in, and once you've logged in, you will be able to see the React prompt, which is the reason plus act prompt. This is the high-level system prompt which we've used in the app. So what does it say? Let's go through it step by step. So we are saying, answer the following questions as best as you can. You have access to the following tools. And all the tools that we've written, we are providing it all in a string format. If you're wondering when we did that, we did not. Our helper functions did that. All right. So all of our tools are provided. Next, we're instructing the LLM to follow this format. So first, the input question, we're telling the LLM it must answer this, and down here, we can also see that we're providing the question right here. So once it understands the question, we are telling the LLM to first think. So this is thought or reason. Basically think about what is the next step. And that's what's written here. You should always think about what to do before doing it. Once it thinks, it then needs to take action. So the action to take should be one of these tool names. So the name of the tools will be provided here with our helper methods. So once it knows the action it is going to take, the action inputs or the inputs to the tools, and finally, it is going to look at the result. So once it knows the action it is going to take, the action inputs or the inputs to the tools, and finally, it is going to look at the result, and that's what observation is right here. It's going to see, well, do we have the final answer or do we have to repeat the cycle again? And once it has the answer, it then proceeds to the final answer. Just like we saw in the terminal, this cycle of thought, action, observation continues until the agent is confident it has solved each part of your prompt. It's like watching a detective walk through clues one by one. And this brings us to the end of the course. This course has already gone on for too long, but I believe that we've learned everything important in LangChain to be able to get started with building AI applications. So you might notice that we've used a lot of helper functions and pre-built prompts from the repository right here. I'm also going to make a separate video next where we're going to be deep diving into agent creation without the help of any of these existing helper methods. So no helper functions, no pre-made prompts, just pure agent creation. Okay, so that will give you a much deeper understanding of how agents work and how agents think. Also, I am posting several videos per week, and if you haven't subscribed, do subscribe so that you'll be notified. So thank you very much for watching, and I'll see you in the next video.